there is a building in Rome that has stood for nearly 2,000 years. Its dome is the largest unreinforced concrete dome in the world. It has no steel reinforcement, no internal skeleton, no modern engineering supports of any kind. It is made entirely of concrete, a concrete that was poured into wooden forms by Roman labourers in the 2nd century of the Common Era, and it has survived earthquakes, floods, wars, neglect, and nearly 20 centuries of weather, without cracking, without crumbling, and without requiring any significant structural repair. The building is the Pantheon, and the concrete from which it is built is stronger today than it was when it was poured. That last sentence is worth reading again. The concrete is stronger today than when it was poured. Not weaker, not degraded, not slowly falling apart as modern concrete inevitably does. Stronger. The chemical processes that were set in motion when the Roman builders mixed their ingredients and poured the material into the formwork have continued for 2,000 years, and they have made the concrete harder and more durable with each passing century. The Pantheon is not merely surviving, it is improving. Modern concrete, by contrast, begins to degrade almost as soon as it is poured. The Portland cement, that is the basis of virtually all modern concrete construction, is subject to a process of chemical deterioration that causes it to crack, to spall, and to lose structural integrity over a period of decades. The expected lifespan of a modern concrete structure is typically between 50 and 100 years, after which the structure requires major repair or replacement. The reinforcing steel that is embedded in modern concrete to provide tensile strength is itself a source of deterioration, because the steel corrodes over time, expanding as it rusts and cracking the concrete from within. The infrastructure of the modern world, the bridges, the highways, the buildings, the dams that are built of reinforced concrete, is slowly falling apart, and the cost of maintaining and replacing this infrastructure runs into the trillions of dollars worldwide. The Romans did not have this problem. Their concrete did not crack, it did not spall, it did not deteriorate over time. Their harbour structures, built in direct contact with seawater, which is one of the most corrosive environments on Earth, have survived for 2,000 years in conditions that would destroy modern concrete in a matter of decades. Their aqueducts, their bridges, their foundations, their walls have endured for centuries longer than any modern concrete structure can be expected to last. And for over 1,500 years, the recipe for this extraordinary material was lost. By the end of tonight, you are going to understand what Roman concrete was, how it was made, why it was so much more durable than modern concrete, and what modern scientists have discovered about the extraordinary chemistry that gives it its remarkable properties. You are going to learn about the specific ingredients that the Romans used, the specific chemical processes that made their concrete superior to ours, and the specific scientific discoveries of the 21st century that have finally begun to explain how a material produced by ancient builders with no knowledge of chemistry could outperform the products of modern materials science. And you are going to confront a question that should trouble every engineer and every builder in the modern world. If the Romans could make concrete that lasted for 2,000 years, why can we not do the same? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Pantheon has stood for nearly 2,000 years. Modern concrete structures are designed to last for 50 to 100 years. The Romans knew something about concrete that we forgot, something that we are only now beginning to rediscover. The material that built an empire, that supported the most ambitious construction projects of the ancient world, that endured for millennia, while our own buildings crumble around us, was lost for 1,500 years. And the story of how it was lost and how it is being rediscovered is one of the most astonishing stories in the history of materials science. Now, let us begin. The contrast between the ancient achievement and the modern failure is one of the most striking paradoxes in the history of materials science. We live in an era of extraordinary technological capability, an era in which we can manipulate matter at the atomic level, in which we can design materials with specific properties using computational modeling, in which we can analyze the composition and the structure of any substance with a precision that would have been inconceivable to the ancient world. And yet, for all of our capability, we cannot produce a concrete that matches the durability of a material that was mixed by hand and poured by labourers who had no understanding of chemistry, no knowledge of mineralogy, and no theory of materials science to guide their work. The implications of this failure extend far beyond the specific question of concrete. They touch on fundamental assumptions about the nature of progress, about the relationship between scientific knowledge and practical capability, and about whether the trajectory of human technology is always upward, or whether it can, in specific and significant ways, move backward. The story of Roman concrete is a story about a material, but it is also a story about knowledge, about how knowledge is created and how it is lost, about the gap between understanding and doing, and about the humbling recognition that the people who came before us were, in some ways, better at building than we are. The questions raised by the Roman concrete story are not comfortable ones for the modern construction industry or for the modern world. How is it possible that a civilization that fell nearly 1600 years ago could produce a material that outperforms the material that the most advanced civilization in human history relies upon? How is it possible that the chemistry of 2,000-year-old concrete can teach us something that the chemistry of modern concrete has missed? And how is it possible that the solution to one of the most expensive and most environmentally damaging problems in modern industry, the deterioration of concrete infrastructure, has been sitting in front of us, literally under our feet, in the ruins of the ancient world, for all this time? To understand Roman concrete, we must first understand the scale of the Roman construction enterprise and the role that concrete played in making it possible. The Roman Empire was the most ambitious building civilization in the history of the ancient world, and concrete was the material that made its ambitions achievable. Without concrete, the Romans could not have built the structures that defined their civilization. The aqueducts, the harbours, the roads, the bridges, the public buildings, and the monumental architecture that still dot the landscape of Europe, North Africa, and the Middle East 2,000 years after they were constructed. The history of concrete begins long before the Romans. The use of cementitious materials, substances that harden when mixed with water and that can bind together aggregates of sand and gravel to form a solid mass, has been documented in various forms for thousands of years. The ancient Egyptians used a form of gypsum-based mortar in the construction of the pyramids. The builders of the ancient Near East used lime-based mortars and plasters for construction and for waterproofing. The ancient Greeks used a lime-based mortar that was effective for some applications, but that lacked the strength and the durability that would characterize the Roman material. The Roman innovation was the discovery that the addition of a specific volcanic ash, known as pozzolana, to a mixture of lime and water produced a material with properties that were fundamentally different from and far superior to the lime mortars that had been used by earlier civilizations. The key property that pozzolana imparted to the mixture was hydraulic setting, the ability to harden and to develop strength even when submerged in water. This property was transformative because it allowed the Romans to build structures in water and in wet environments, structures that no previous civilization had been able to construct using cementitious materials. The term pozzolana derives from the town of Pozzuoli, near Naples, in the volcanic region of Campania, which was one of the most important sources of the volcanic ash that the Romans used in their concrete. The volcanic deposits of Campania, which were produced by the eruptions of Mount Vesuvius and other volcanoes in the region, contained minerals, particularly a family of minerals called zeolites, that reacted chemically with lime and water to produce a hard, durable, waterproof material. The Romans discovered this reaction empirically, through observation and experimentation, without any understanding of the chemistry that underlay it. They knew that the addition of the volcanic ash from the Pozzuoli region to their lime mixture produced a superior building material. They did not know why. The Roman architect and engineer Vitruvius, writing in the 1st century before the Common Era, provided the most detailed surviving description of Roman concrete production in his treatise De Architectura. Vitruvius described the specific materials that were used, including the volcanic ash, the lime, the water, and the aggregates of rock and broken pottery that were mixed together to form the concrete. He described the specific proportions in which the materials were combined, recommending a mixture of 1 part lime to 3 parts pozzolana for most applications, with a modified ratio for underwater construction. And he described the specific procedures that were followed during the mixing and the placement of the concrete, including the importance of thorough mixing, proper curing, and the use of formwork to shape the material as it hardened. Vitruvius's description, while invaluable, is not a complete recipe for Roman concrete. His treatise is a general guide to architectural practice, not a detailed technical manual, and it does not include the specific information about temperatures, curing times, water ratios, and other variables that would be needed to reproduce Roman concrete under controlled conditions. The gaps in Vitruvius's description have been one of the challenges that modern researchers have faced in their efforts to understand and to reproduce the Roman material. The scale of the Roman concrete construction enterprise was enormous. Concrete was used in virtually every type of Roman construction, from the foundations of ordinary houses to the vaults and domes of the most ambitious public buildings. The Roman road system, which extended for approximately 400,000 kilometers across the empire, used concrete in its foundations and in the construction of bridges and other structures along the routes. The Roman aqueduct system, which supplied water to cities across the empire through an elaborate network of channels, tunnels, and bridges, used concrete extensively in the construction of the channels, the reservoirs, and the distribution systems. The Roman harbours, which were the most sophisticated maritime facilities in the ancient world, used concrete for the construction of breakwaters, docks, and underwater foundations. The Pantheon, which we have already mentioned, is the most famous and the most impressive example of Roman concrete construction. The building was constructed during the reign of the Emperor Hadrian, approximately between 118 and 128 of the Common Era, and it features a dome with an interior diameter of approximately 43.3 meters, a span that was the largest in the world for over 1,300 years until the construction of the dome of the Florence Cathedral in the 15th century. The dome of the Pantheon is made entirely of unreinforced concrete, poured in horizontal layers, with the density of the concrete decreasing toward the top of the dome, where lighter volcanic rock was used as aggregate to reduce the weight. The engineering of the Pantheon dome demonstrates a sophisticated understanding of the properties of concrete and of the principles of structural engineering. The builders varied the composition of the concrete at different levels of the dome, using denser, heavier aggregate in the lower portions, where the structural loads were greatest, and lighter, less dense aggregate in the upper portions, where the reduction of weight was more important. The coffers, the recessed panels that decorate the interior of the dome, served both an aesthetic and a structural function, reducing the weight of the dome without reducing its strength. And the oculus, the circular opening at the apex of the dome, which has a diameter of approximately 8.7 meters, serves both as a source of light and as a structural release that reduces the stress at the top of the dome. The Roman harbours provide another dramatic example of the performance of Roman concrete in extreme environments. The harbour structures at Caesarea Maritima on the coast of modern Israel were built by King Herod the Great in the late 1st century, before the Common Era, using a technology that the Romans called opus caementicium, a concrete that was poured directly into the sea using wooden formwork. The harbour structures at Caesarea, which include massive breakwaters that extend hundreds of meters into the sea, were built in one of the most challenging construction environments imaginable, directly in contact with salt water, subject to the constant action of waves and currents, and exposed to the chemical attack of dissolved salts. Despite these extreme conditions, the concrete of the Caesarea harbour has survived for over 2,000 years, and recent investigations have shown that it is, in many respects, stronger and more durable than it was when it was first poured. The survival of Roman concrete structures in marine environments is one of the most remarkable and most scientifically significant aspects of the material's performance. Modern Portland cement concrete deteriorates rapidly when exposed to seawater because the dissolved salts in the seawater react with the cement minerals, producing expansive compounds that crack the concrete from within. The expected lifespan of modern concrete in a marine environment is typically less than 50 years, and the maintenance and the replacement of marine concrete structures is one of the most expensive and most challenging problems in modern civil engineering. The fact that Roman concrete has survived for 2,000 years in the same environment that destroys modern concrete in decades is a datum that demands explanation. The production of Roman concrete required the organization of a complex supply chain that brought together raw materials from different parts of the empire. The volcanic ash that was the key ingredient of the concrete was obtained from the volcanic deposits of Campania and from other volcanic regions around the Mediterranean, including the island of Santorini in the Aegean Sea, whose volcanic ash was particularly valued for underwater construction. The lime was produced by burning limestone or marble in kilns, a process that required large quantities of fuel, and that was one of the most energy-intensive industrial processes in the Roman world. The aggregates, which included crushed rock, gravel, broken pottery, and broken brick, were obtained from local sources and were selected according to the specific requirements of the construction project. The labor force that produced and placed the concrete was organized according to the hierarchical structure of the Roman construction industry, which included architects, engineers, foremen, skilled workers, and unskilled laborers. The mixing and the placement of concrete was physically demanding work that required the coordination of large teams of workers who mixed the ingredients by hand, transported the wet concrete to the construction site, and placed it in the formwork in a continuous operation that had to be completed before the concrete began to set. The scale of the labor required for the largest concrete construction projects, such as the Pantheon or the Colosseum, was enormous, involving hundreds or thousands of workers over a period of months or years. The Roman concrete tradition was not static. It evolved over the centuries as the Romans gained experience with the material and as they adapted their techniques to meet the changing demands of their construction projects. The earliest Roman concrete, which dates to the 3rd century before the Common Era, was a relatively crude material that was used primarily for foundations and for fill behind stone-facing walls. The concrete of the late Republic and the early Empire, which includes some of the most famous Roman structures, was a more refined material that was used for vaults, domes, and other structurally ambitious applications. And the concrete of the later Empire incorporated innovations in the composition of the mix and in the techniques of placement that reflected the accumulated experience of centuries of construction practice. The transition from stone and brick construction to concrete construction was one of the most important developments in the history of Roman architecture. Before the widespread adoption of concrete, Roman buildings were constructed primarily of cut stone or of brick, materials that were expensive, labor-intensive, and limited in the forms that they could produce. The adoption of concrete freed the Roman builders from these limitations, allowing them to construct buildings with curves, vaults, and domes that would have been impossible to achieve with stone or brick alone. The revolution in architectural form that characterized the late Republic and the Empire, including the development of the barrel vault, the groin vault, and the dome, was made possible by concrete, and the architectural achievements that define the Roman building tradition are, in a fundamental sense, achievements of concrete technology. The geological context of the Roman concrete tradition provides essential background for understanding why the material worked so well. The Italian peninsula sits on one of the most volcanically active regions in Europe, and the volcanic deposits that are scattered across central and southern Italy provided the Romans with a ready supply of the pozzolanic materials that were essential for their concrete. The volcanic history of the region stretches back millions of years, and the specific eruptions that produced the deposits used by the Romans occurred tens of thousands to hundreds of thousands of years before the founding of Rome. providing ample time for the volcanic materials to weather and to develop the specific mineral compositions that made them effective as pozzolanic additives. The specific characteristics of the Italian volcanic deposits that made them suitable for concrete production include their high content of reactive silica and alumina, their fine particle size, and their content of zeolite minerals that are particularly reactive with lime and water. The volcanic deposits of the Phlegrean Fields, the region around Pozzuoli that gave the material its name, are particularly rich in zeolites and other reactive minerals, and the concrete made from these deposits was considered the highest quality by the Roman builders. The deposits of other volcanic regions, including the areas around Rome, around Mount Vesuvius, and on the island of Santorini in the Aegean, were also used for concrete production, and the specific properties of the concrete varied depending on the source of the volcanic ash. The discovery of the pozzolanic reaction was almost certainly accidental, the result of the observation that mortar made with volcanic ash from certain regions was stronger and more durable than mortar made with ordinary sand. The Romans, who were pragmatic and observational in their approach to technology, would have noticed the superior performance of the volcanic ash mortar and would have adopted it as their standard practice without needing to understand the chemical basis of its superior performance. The practical significance of the discovery was enormous because it provided the Romans with a building material that could be used for a far wider range of applications than the lime mortars that had been available to earlier civilizations. The production of lime, which was the other essential ingredient of Roman concrete, was an industrial process that required significant resources, and that was one of the most energy-intensive activities in the Roman economy. Lime is produced by heating limestone, calcium carbonate, to a temperature of approximately 900 degrees Celsius in a kiln, driving off carbon dioxide and leaving behind quicklime, calcium oxide. The quicklime is then either slaked with water to produce slaked lime, calcium hydroxide, or, as the Massic team has suggested, added directly to the concrete mix in its unslaked form. The production of lime required large quantities of limestone and large quantities of fuel, typically wood or charcoal, and the Roman lime kilns, many of which have been excavated by archaeologists, were substantial industrial installations that were operated by specialized workers. The aggregates that were used in Roman concrete, including crushed rock, gravel, broken brick, and broken pottery, were selected according to the specific requirements of the construction project. For ordinary construction, local stone and gravel were used, providing a strong and durable aggregate that was readily available. For specialized applications, such as the construction of the Pantheon Dome, lightweight volcanic materials, including pumice and tuff, were used to reduce the weight of the concrete. The selection of the appropriate aggregate for each application was an important part of the builder's skill, and the quality of the aggregate was a significant factor in the performance of the finished concrete. The mixing of Roman concrete was performed by hand, using tools that are familiar to modern builders: shovels, hoes, and mixing troughs. The ingredients were combined with water and mixed until the desired consistency was achieved, and the wet concrete was then transported to the construction site and placed in the formwork. The formwork, which was typically made of wood, defined the shape of the finished structure, and the concrete was poured into the formwork in layers, with each layer being tamped or vibrated to consolidate the material and to remove air pockets. The curing of the concrete, the process by which the material develops its strength, required keeping the concrete moist for a period of days or weeks after placement, and the Roman builders used various techniques, including covering the concrete with wet sand or straw, to maintain the moisture that was needed for proper curing. The institutional infrastructure that supported the Roman concrete construction enterprise was one of the most sophisticated industrial organizations in the ancient world. The Roman construction industry employed thousands of workers at multiple levels of skill and responsibility, from the architects and the engineers who designed the structures to the foremen who supervised the work, to the laborers who mixed and placed the concrete. The organization of this workforce, which required the coordination of specialized activities across large construction sites over periods of months or years, was itself a significant achievement of management and logistics. The Roman military was one of the most important institutions in the development and the dissemination of concrete construction techniques. The Roman legions, which were responsible for the construction of roads, bridges, fortifications, and other military infrastructure across the empire, were among the most experienced and the most skilled concrete builders in the Roman world. The engineering knowledge that the legions possessed was transmitted through the military training system, which provided a systematic program of instruction in construction techniques that ensured a consistent level of skill across the empire. The dispersal of the legions to every corner of the Roman world ensured that concrete construction techniques were available wherever Roman authority extended. The public works programs of the Roman emperors were the primary drivers of the most ambitious concrete construction projects. The construction of monumental public buildings, such as the Pantheon, the Colosseum, and the Baths of Caracalla, required enormous investments of resources and labour that only the imperial government could provide. The emperors funded these projects not only for their practical utility, but also for their political significance as demonstrations of imperial power and generosity that reinforced the legitimacy of the ruling dynasty. The scale and the ambition of these imperial construction projects pushed the boundaries of concrete technology, driving innovations in the composition of the concrete, the design of the structures, and the techniques of construction. The Roman baths of Caracalla, built in the early 3rd century of the Common Era, are among the most impressive examples of Roman concrete construction. The baths, which covered an area of approximately 11 hectares and which could accommodate an estimated 1,600 bathers simultaneously, featured enormous vaulted halls, heated pools, cold plunges, gymnasiums, and gardens, all constructed of concrete. The vaults of the main bathing hall, which spanned approximately 25 meters, were among the largest concrete vaults in the Roman world, and their construction required sophisticated engineering and a deep understanding of the behavior of concrete under load. The Basilica of Maxentius, built in the early 4th century of the Common Era, and one of the last great concrete buildings of the Roman tradition, featured vaults that spanned approximately 25 meters and that rose to a height of approximately 35 meters. The basilica, which was one of the most ambitious architectural projects of the late Roman period, demonstrated that the Roman concrete tradition had continued to develop and to innovate throughout the centuries of the empire, producing structures of increasing size and increasing complexity. The partial collapse of the basilica, which lost 2/3 of its original structure in an earthquake in the 9th century, provides evidence for the structural limits of unreinforced concrete construction. But the surviving portion, which still stands in the Roman Forum, demonstrates the extraordinary durability of the material. The Roman aqueduct system, which was one of the largest and most sophisticated water supply systems in the ancient world, relied heavily on concrete for the construction of channels, reservoirs, distribution tanks, and other components. The total length of the Roman aqueduct system that supplied the city of Rome alone has been estimated at approximately 500 kilometers, and the construction of this system required enormous quantities of concrete that were produced and placed over a period of several centuries. The aqueducts of other Roman cities, including the famous Pont du Gard near Nimes in France and the aqueduct of Segovia in Spain, demonstrate the range and the versatility of Roman concrete construction in hydraulic applications. The maritime applications of Roman concrete deserve particular emphasis because they demonstrate the material's performance in the most demanding environment that any construction material can face. The Roman harbour at Caesarea Maritima, which was one of the largest artificial harbours in the ancient world, was constructed using a technique in which wet concrete was poured directly into the sea through wooden formwork that was positioned on the sea floor. The concrete set and hardened underwater, a feat that was possible only because of the hydraulic setting property that the volcanic ash imparted to the mixture. The construction of the Caesarea harbour required sophisticated engineering and meticulous planning. The formwork, which consisted of large wooden caissons that were floated into position and then sunk to the sea floor, had to be precisely positioned and securely anchored to withstand the forces of the waves and the currents while the concrete was poured and while it set. The concrete was mixed on shore and transported to the formwork by boat, where it was poured through the open top of the caissons and allowed to settle to the bottom, filling the formwork from the bottom up. The process had to be completed quickly enough to prevent the concrete from setting before it reached the bottom of the formwork, and the logistics of the operation required the coordination of dozens of workers and boats. The concrete of the Caesarea harbour has been extensively studied by marine archaeologists and by materials scientists, and the results of these studies have provided some of the most important evidence for the superior performance of Roman concrete in marine environments. The core samples that have been taken from the harbour structures show that the concrete is dense, well consolidated, and free of the cracks and the voids that characterize deteriorating modern concrete. The mineral phases that have been identified in the concrete include aluminum tobermarite and philipsite, the same minerals that Marie Jackson and her colleagues identified in the concrete of the harbour at Portus Cosanus, confirming that the formation of these strengthening minerals is a general feature of Roman marine concrete, rather than a phenomenon specific to a single site. The harbour structures of other Roman sites, including the harbours at Baiae, Portus and Alexandria, have also been studied, and the results have confirmed the general pattern of superior durability that has been observed at Caesarea. The concrete at each of these sites shows the same general characteristics: a dense, well-consolidated matrix containing the products of the pozzolanic reaction, supplemented by the long-term formation of tobermarite and philipsite that strengthens the material over time. The consistency of these findings across multiple sites and multiple regions demonstrates that the superior durability of Roman marine concrete is not an accident of specific local conditions, but a systematic consequence of the Roman approach to concrete production. The Roman approach to quality control in concrete production, while not documented in the formal terms of modern quality management, was clearly effective, as evidenced by the consistently high quality of the surviving Roman concrete structures. The consistency of the material across different sites and different periods suggests that the Roman builders maintained standards of practice that ensured a minimum level of quality in the concrete they produced. These standards were presumably transmitted through the apprenticeship system that trained the builders and the engineers of the empire, and they were enforced by the supervision of experienced foremen who were responsible for overseeing the mixing, the placement, and the curing of the concrete. The question of how the Roman builders tested the quality of their concrete is one that has been addressed through both archaeological and literary evidence. Vitruvius describes the visual and tactile tests that were used to evaluate the quality of the pozzolana, including the examination of the color, the texture, and the weight of the material. The pozzolana from certain sources was known to be superior to pozzolana from other sources, and the selection of the appropriate pozzolana for a specific application was an important aspect of the builder's expertise. The testing of the finished concrete was presumably conducted through observation of the material's performance during and after the curing process. Concrete that cracked during curing, that failed to develop adequate strength, or that showed signs of deterioration would have been identified by the builders and would have informed their future practice. The accumulation of this kind of empirical knowledge over centuries of construction experience produced a body of practical understanding that guided the Roman builders in their selection of materials, their mixing procedures, and their curing practices, ensuring a level of quality that has proven to be extraordinary in its durability. The specific proportions of the Roman concrete mix have been the subject of considerable research, and the results have revealed that the proportions varied depending on the application. For ordinary construction, a ratio of approximately 1 part lime to 3 parts pozzolana was typically used, consistent with the recommendation of Vitruvius. For underwater construction, a richer mix with a higher proportion of pozzolana was sometimes used to ensure that the concrete would set properly in the presence of water. For lightweight applications, such as the upper portions of domes, the proportion of aggregate was increased, and the aggregate itself was replaced with lighter materials, such as pumice or tuff. The relationship between the Roman concrete tradition and the traditions of other ancient civilizations provides comparative context for understanding the uniqueness of the Roman achievement. The ancient Egyptians used a gypsum-based mortar that hardened relatively quickly, but that was not hydraulic, and that could not be used for underwater construction. The ancient Mesopotamians used bitumen, a naturally occurring petroleum product, as a waterproofing agent and as a binding material, but bitumen does not develop the strength and the durability that characterize cementitious materials. The ancient Chinese developed a variety of lime-based mortars and concretes that were used for construction and for waterproofing, and some of these Chinese materials exhibit properties that are comparable to those of Roman concrete, though the Chinese tradition developed independently and used different raw materials. The Indian tradition of lime-based construction, which produced the impressive structures of the Mughal period and earlier, used lime mortars that were sometimes combined with volcanic or burnt clay additives that provided some pozzolanic properties. The Indian builders also developed techniques of lime sugar mortars, in which organic compounds were added to the lime mix to improve its workability and its durability. These Indian techniques, while effective for their intended purposes, did not produce materials with the specific combination of properties that characterized Roman concrete, and they represent a parallel but distinct tradition of cementitious construction. The uniqueness of the Roman concrete tradition lies not in any single feature, but in the specific combination of features that the material possessed. The hydraulic setting property that allowed it to be used underwater, the pozzolanic reaction that produced a more durable cementitious phase, the self-healing mechanism that repaired cracks and maintained structural integrity over time, and the long-term formation of strengthening minerals that improved the material's properties over centuries and millennia. No other ancient civilization produced a material that combined all of these features, and the Roman achievement in concrete technology is therefore unique in the history of pre-modern construction. The transmission of the Roman concrete tradition during the period of the late Empire and the early medieval period is an area that has been investigated by historians and archaeologists. The concrete construction tradition continued in the Eastern Roman Empire, the Byzantine Empire, after the fall of the Western Empire, and Byzantine buildings such as the Hagia Sophia in Constantinople used concrete in their construction. The Byzantine concrete, while it was produced using techniques that were derived from the Roman tradition, was generally of lower quality than the best Roman concrete, reflecting the gradual decline in the quality of the available materials and the loss of the specific skills that had characterized the Roman builders at the height of the empire. The medieval period in Western Europe saw a dramatic decline in the use of concrete as a construction material. The loss of access to the volcanic ash from Campania, the loss of the engineering knowledge that had been needed to design and to construct concrete structures, and the loss of the institutional infrastructure that had organized the large-scale construction projects of the Roman period, all contributed to the abandonment of concrete as a primary building material. The medieval builders of Western Europe returned to stone and brick construction, using lime mortars that were effective for joining cut stone, but that did not possess the structural properties of Roman concrete. The revival of interest in hydraulic methods in the 18th century, which eventually led to the development of Portland cement by Joseph Aspdin, was not directly connected to the Roman tradition. Aspin and his contemporaries were working within the European lime mortar tradition, seeking to develop a cement that would harden in the presence of water, and they were not primarily interested in the properties of ancient Roman concrete. The result of their work, Portland cement, was a new material that solved the problem of hydraulic setting but that did not replicate the specific combination of properties that had characterized the Roman material. The development of Portland cement was therefore a parallel innovation rather than a rediscovery of the Roman recipe, and the specific advantages of the Roman approach were not recognized until modern analytical techniques revealed the superior durability and the self-healing properties of the ancient material. The core problem with Roman concrete is not that we cannot make concrete. We make enormous quantities of concrete every year. Modern concrete production is one of the largest industries in the world, producing approximately 4.4 billion metric tons of cement annually and consuming vast quantities of energy, water, and raw materials. The problem is that the concrete we make is fundamentally inferior to the concrete that the Romans made, in at least one critical respect: durability. Our concrete cracks, spalls, and deteriorates over a period of decades. Their concrete has lasted for millennia, and for most of the modern era, we did not understand why. The chemistry of modern Portland cement, which was invented by Joseph Aspin in 1824, and which is the basis of virtually all modern concrete, is well understood. Portland cement is produced by heating a mixture of limestone and clay to a temperature of approximately 1400 to 1500 degrees Celsius in a rotary kiln, producing a hard, grey material called clinker, which is then ground into a fine powder. When the powder is mixed with water, a series of chemical reactions, known collectively as hydration, produces a hard, stone-like material that binds together the aggregate, the sand and gravel, that constitutes the bulk of the concrete. The hydration reactions that produce the strength of Portland cement are well characterized. The primary reaction involves the minerals tricalcium silicate and dicalcium silicate, which react with water to form calcium silicate hydrate, the gel-like substance that is the primary source of concrete's strength, and calcium hydroxide, a byproduct that is relatively weak and that is vulnerable to chemical attack. The calcium silicate hydrate forms a network of microscopic fibers that bind the cement particles and the aggregate together, producing a rigid stone-like mass. The strength of the concrete depends on the density and the continuity of the calcium silicate hydrate network, which in turn depends on the water-to-cement ratio, the curing conditions, and the quality of the raw materials. But here is the problem. The hydration reactions that produce the strength of Portland cement are essentially complete within the first few months after the concrete is poured. After this initial period, the concrete does not continue to gain strength. In fact, it begins to lose strength as the calcium hydroxide that was produced by the hydration reactions is gradually dissolved by water, particularly by acidic water or by seawater, creating voids and weaknesses in the concrete matrix. The reinforcing steel that is embedded in modern concrete to provide tensile strength is also vulnerable to corrosion, particularly in marine environments or in environments where the concrete is exposed to de-icing salts. And the corrosion of the steel produces expansive rust that cracks the concrete from within. The deterioration of modern concrete is a global problem of enormous economic and social significance. The American Society of Civil Engineers has estimated that the cost of repairing and replacing the deteriorating concrete infrastructure of the United States alone is in the trillions of dollars, and similar problems exist in every country that relies on reinforced concrete for its infrastructure. The bridges, the highways, the tunnels, the dams, the buildings, and the other concrete structures that constitute the backbone of modern civilization are slowly falling apart, and the cost of maintaining them is consuming an ever-increasing share of public resources. Roman concrete does not have this problem. The chemistry of Roman concrete is fundamentally different from the chemistry of Portland cement, and the differences explain why the Roman material is so much more durable. The key difference is the role of the pozzolanic reaction, the chemical reaction, between the volcanic ash and the lime that produces the cementitious properties of the Roman material. The pozzolanic reaction produces a different set of mineral phases than the hydration of Portland cement, and these mineral phases have different properties, particularly with respect to their stability in the presence of water. The primary product of the pozzolanic reaction is a calcium aluminum silicate hydrate gel which is different in composition and in structure from the calcium silicate hydrate that is the primary product of Portland cement hydration. The calcium aluminum silicate hydrate gel is more stable in the presence of water, more resistant to chemical attack, and more durable over long periods of time than the calcium silicate hydrate of Portland cement. The pozzolanic reaction also produces less calcium hydroxide than the hydration of Portland cement, reducing the amount of the vulnerable byproduct that can be dissolved by water, and that contributes to the deterioration of the concrete. And it gets worse for modern concrete. The research that has been conducted on Roman concrete over the past 2 decades has revealed that the Roman material possesses properties that go far beyond simple durability. The Roman concrete is not merely resistant to deterioration, it is actively self-healing, capable of repairing cracks and voids that develop in its structure through the continued growth of mineral phases that fill the cracks and restore the integrity of the material. The self-healing property of Roman concrete is one of the most extraordinary discoveries in the history of materials science. The mechanism of self-healing was identified by researchers at the Massachusetts Institute of Technology and at other institutions who discovered that the lime clasts, small fragments of incompletely mixed lime that are present in Roman concrete, dissolve when water enters the cracks in the material, and that the dissolved calcium reacts with the surrounding pozzolanic material to produce new cementitious compounds that fill the cracks and restore the structural integrity of the concrete. The process is automatic, requiring no human intervention, and it continues for as long as the lime clasts and the pozzolanic material are present in the concrete, which can be centuries or even millennia. The discovery of the self-healing mechanism was published in 2023 by a team led by Adma Masick of the Massachusetts Institute of Technology, and it has been widely regarded as one of the most important discoveries in the history of concrete science. The discovery explained a phenomenon that had puzzled researchers for decades. The observation that Roman concrete appears to get stronger over time rather than weaker. The self-healing mechanism provides a physical and chemical explanation for this observation, showing that the cracks and the voids that inevitably develop in concrete over time are repaired by the continued chemical reactions between the lime clasts and the pozzolanic material, producing new mineral phases that fill the cracks and that increase the density and the strength of the material. The lime clasts that are the key to the self-healing mechanism were previously regarded as defects, evidence of poor mixing or careless construction. The conventional assumption among concrete scientists was that the ideal concrete mix was one in which the lime was completely dissolved and uniformly distributed, and the presence of undissolved lime clasts was therefore interpreted as a sign of inadequate mixing. The Masick team's discovery overturned this assumption, showing that the lime clasts were not defects but features, integral components of a self-healing system that was, perhaps inadvertently, built into the Roman concrete through the use of a mixing technique that deliberately or inadvertently left small fragments of quicklime undissolved in the mix. The question of whether the self-healing property of Roman concrete was intentional or accidental is one that cannot be answered with certainty. The Romans did not understand the chemistry of their concrete, and they could not have known that the lime clasts in their mix would provide a self-healing mechanism that would sustain the durability of the material for millennia. It is possible that the mixing technique that left the lime clasts undissolved was a deliberate practice, developed through trial and error, that the Romans adopted because they observed that concrete made with this technique was more durable than concrete made with more thorough mixing. It is also possible that the lime clasts were simply the result of the practical limitations of hand mixing, which could not achieve the uniform distribution of ingredients that modern mechanical mixing can produce. In either case, the result was the same: a concrete with a built-in self-healing mechanism that has sustained its integrity for 2,000 years. The interaction between Roman concrete and seawater is another area where the ancient material has proven to be superior to modern concrete in ways that are only now being understood. When modern Portland cement concrete is exposed to seawater, the dissolved salts in the water react with the cement minerals, producing expansive compounds, particularly ettringite and thormosite, that crack the concrete from within. This process, known as sulfate attack, is one of the primary causes of concrete deterioration in marine environments, and it is the reason why modern marine concrete structures have such limited lifespans. When Roman concrete is exposed to seawater, a fundamentally different process occurs. Instead of producing destructive expansive compounds, the seawater reacts with the volcanic ash and the lime in the Roman concrete to produce new mineral phases, specifically a type of mineral called aluminum tobermorite and a related mineral called philipsite, that fill the voids and the pores in the concrete, increasing its density, its strength, and its resistance to further chemical attack. The formation of these minerals is a slow process that occurs over decades and centuries, and it is the primary mechanism by which Roman marine concrete gains strength over time, rather than losing it. The discovery of aluminum tobermorite and philipsite in Roman marine concrete was made by a team led by Marie Jackson of the University of Utah, who published her findings in 2017. Jackson's research, which used X-ray synchrotron microdiffraction and other advanced analytical techniques to study samples of Roman marine concrete from the harbour at Portus Cosanus in Italy, revealed the presence of these minerals within the structure of the concrete and demonstrated that they were the products of the long-term interaction between the concrete and the seawater. Jackson's discovery was a major advance in the understanding of Roman concrete because it provided a specific mineralogical mechanism for the material's extraordinary durability in marine environments. The formation of aluminum tobermorite in Roman concrete is particularly significant because tobermorite is a mineral that is actively sought by modern concrete scientists for its strength-enhancing properties. Tobermorite is a crystalline form of calcium silicate hydrate that is denser, more stable, and more durable than the amorphous calcium silicate hydrate that is produced by the hydration of Portland cement. Modern concrete scientists have attempted to produce tobermorite in concrete by various means, including the use of high temperatures and high pressures, but they have not been able to produce it under the ambient conditions that characterize ordinary concrete construction. The Romans, apparently without trying, produced concrete in which tobermorite forms naturally over time through the interaction of the concrete with the surrounding water. But here is what makes this truly terrifying. Modern concrete production is one of the largest sources of carbon dioxide emissions in the world. The production of Portland cement, which requires the heating of limestone and clay to approximately 1400 to 1500 degrees Celsius, releases approximately 800 kilograms of carbon dioxide for every ton of cement produced. The global cement industry is estimated to be responsible for approximately 8% of total global carbon dioxide emissions, making it one of the most significant contributors to climate change. The Roman concrete recipe, which uses lime that is burned at lower temperatures and which incorporates volcanic ash that requires no heating at all, has a significantly lower carbon footprint than the production of Portland cement. The adoption of a Roman-inspired concrete recipe could therefore reduce the carbon emissions of the construction industry, while simultaneously producing a more durable material that would reduce the need for the frequent repair and replacement that characterizes modern concrete infrastructure. The detailed mechanism of the pozzolanic reaction, which is the foundation of the superior performance of Roman concrete, deserves more thorough examination. The pozzolanic reaction is a chemical reaction between the silica and the alumina in the volcanic ash and the calcium hydroxide that is produced by the lime in the presence of water. The products of this reaction are calcium silicate hydrate and calcium aluminum silicate hydrate gels, which are the primary cementitious phases in Roman concrete and which are responsible for the material's strength and durability. The pozzolanic reaction differs from the hydration of Portland cement in several important ways. First, the pozzolanic reaction is slower than Portland cement hydration, requiring weeks or months to develop significant strength rather than the days that Portland cement requires. This slower reaction rate was not a disadvantage for the Romans, who were not under the time pressure that characterizes modern construction, and it may have been an advantage because the slower reaction allows the cementitious phases to develop in a more ordered and more stable configuration. Second, the products of the pozzolanic reaction are chemically different from the products of Portland cement hydration. The calcium aluminum silicate hydrate gel that is produced by the pozzolanic reaction is more chemically stable than the calcium silicate hydrate that is produced by Portland cement hydration, particularly in the presence of water and dissolved salts. The greater chemical stability of the pozzolanic products is one of the primary reasons why Roman concrete is more durable than Portland cement concrete, particularly in wet environments and in marine environments where the chemical attack of dissolved salts is a significant cause of deterioration. Third, the pozzolanic reaction produces less calcium hydroxide than the hydration of Portland cement. Calcium hydroxide is the weakest and the most chemically vulnerable phase in concrete, and its dissolution by water or by acidic solutions creates voids and weaknesses in the concrete matrix that contribute to its deterioration. The lower calcium hydroxide content of Roman concrete is therefore another factor that contributes to its superior durability. The specific mineral phases that form in Roman concrete over long periods of time, including aluminum tobermorite and philipsite, are the products of the long-term reactions between the concrete and the water that permeates it. These mineral phases, which form over decades and centuries, fill the pores and the voids in the concrete, increasing its density and its strength and providing additional resistance to chemical attack. The formation of these minerals is a slow, continuous process that has no analogue in Portland cement concrete, and it is one of the most remarkable and most distinctive features of the Roman material. The comparison between the chemical environments within Roman concrete and within Portland cement concrete reveals fundamental differences that explain the divergent long-term performance of the two materials. In Portland cement concrete, the chemical environment is dominated by the calcium hydroxide that is produced by the hydration reactions, creating a highly alkaline pore solution that is initially protective of the steel reinforcement, but that becomes vulnerable to carbonation and to the penetration of chloride ions over time. The loss of the protective alkaline environment around the steel reinforcement leads to corrosion of the steel, which is the primary cause of deterioration in reinforced concrete structures. In Roman concrete, the chemical environment is dominated by the products of the pozzolanic reaction, which are more stable and more resistant to chemical change than the products of Portland cement hydration. The absence of steel reinforcement eliminates the problem of steel corrosion entirely, and the continued formation of mineral phases within the concrete matrix provides ongoing protection against chemical attack. The chemical environment within Roman concrete is therefore self-sustaining and self-protective, a feature that is fundamentally different from the chemical environment within Portland cement concrete, which is inherently unstable and which requires external intervention to maintain. The infrastructure crisis that the modern world faces as a result of the limited durability of Portland cement concrete is one of the most significant challenges of the 21st century. The concrete structures that were built during the great infrastructure boom of the mid-20th century, including highways, bridges, tunnels, dams, and buildings across the developed world, are now reaching the end of their designed lifespans, and the cost of repairing and replacing them is straining the budgets of governments at every level. The United States provides a dramatic example of the scale of the problem. The American Society of Civil Engineers has given the nation's infrastructure a grade of C- in its most recent assessment, citing the deteriorating condition of bridges, roads, dams, and other concrete structures as one of the most urgent problems facing the country. The organization has estimated that the investment needed to bring the nation's infrastructure to a state of good repair is in the trillions of dollars, a figure that reflects the accumulated consequences of decades of underinvestment in maintenance and the inherent limitations of the concrete materials that were used in the original construction. The problem is not limited to the United States. Every country that built its infrastructure with Portland cement concrete during the 20th century faces similar challenges, and the global cost of addressing the concrete infrastructure crisis is measured in the tens of trillions of dollars. The developing world faces an additional challenge because the rapid urbanization and industrialization of countries in Asia, Africa, and Latin America is generating an enormous demand for new concrete construction at the same time that the developed world is struggling to maintain and to replace its existing concrete infrastructure. The environmental dimension of the concrete problem adds urgency to the search for alternatives. The production of Portland cement, which is the primary ingredient of modern concrete, is responsible for approximately 8% of global carbon dioxide emissions, making the cement industry one of the largest individual contributors to climate change. The emissions come from two sources: the combustion of fossil fuels to heat the limestone and clay in the kiln, and the chemical decomposition of the limestone itself, which releases carbon dioxide as a byproduct. The total emissions from the global cement industry are estimated at approximately 2.8 billion metric tons of carbon dioxide per year, a figure that is expected to increase as the demand for concrete in the developing world continues to grow. The search for lower carbon alternatives to Portland cement has therefore become one of the most active areas of research in materials science and in civil engineering, and the principles embodied in Roman concrete, particularly the use of pozzolanic reactions and the incorporation of self-healing mechanisms, are among the most promising avenues of investigation. The question of whether the specific volcanic ash from Campania was essential for the production of high-quality Roman concrete, or whether volcanic ash from other sources could produce similar results, is one of considerable practical importance for the modern application of Roman concrete principles. If the superior performance of Roman concrete is dependent on the specific properties of the Campanian pozzolana, then the modern application of Roman concrete principles would be limited by the availability of this specific material. If, on the other hand, the principles can be applied using volcanic materials from other sources, or using non-volcanic pozzolanic materials such as fly ash or slag, then the potential for widespread modern application would be much greater. The research that has been conducted on this question has produced results that are generally encouraging. While the Campanian pozzolana has specific properties that make it particularly effective, including its high zeolite content and its fine particle size, other volcanic materials have also been shown to produce effective pozzolanic cements. The volcanic ash from Santorini, which the Romans themselves used for marine construction in the eastern Mediterranean, has been shown to produce concrete with properties that are comparable to those of concrete made with Campanian pozzolana. And the modern pozzolanic materials, including fly ash and ground granulated blast furnace slag, have been shown to produce concrete with improved durability compared to conventional Portland cement concrete, though the long-term performance of these modern pozzolanic concretes has not yet been demonstrated over the timescales that have been achieved by the Roman material. The global distribution of volcanic ash deposits is relevant to the potential for widespread adoption of Roman-inspired concrete. Volcanic ash is found on every continent, and many of the world's most rapidly growing urban areas are located in regions with abundant volcanic deposits. The countries of the Pacific Ring of Fire, including Japan, Indonesia, the Philippines, Chile, and the countries of Central America, have access to enormous deposits of volcanic ash that could potentially be used as pozzolanic additives in concrete. The countries of East Africa, which are located along the East African Rift, another zone of intense volcanic activity, also have access to significant volcanic ash deposits. The availability of these volcanic materials suggests that the adoption of Roman-inspired concrete recipes could be feasible on a global scale, using locally available volcanic materials rather than the specific Campanian pozzolana that the Romans used. The testing of volcanic ash from different geographical sources has revealed that the effectiveness of the ash as a pozzolanic additive depends on its specific mineral composition, its particle size distribution, and its degree of weathering. Not all volcanic ash is equally effective, and the selection of the appropriate ash for a specific application requires testing and evaluation. The development of standards and specifications for volcanic ash as a concrete additive is an ongoing process that is being pursued by several standards organizations and research institutions. The study of the microstructure of Roman concrete at the nanometer scale has revealed features that are even more remarkable than the macroscopic properties of the material would suggest. The calcium aluminum silicate hydrate gel that is the primary cementitious phase in Roman concrete has a nanostructure that is distinctly different from the nanostructure of the calcium silicate hydrate in Portland cement concrete. The Roman gel has a more ordered crystal structure, a higher degree of cross-linking between the silicate chains, and a greater incorporation of aluminum into the crystal lattice, all of which contribute to its superior stability and durability. The incorporation of aluminum into the silicate structure of the gel is a particularly important feature because it creates a more rigid and more chemically stable network that is less susceptible to the leaching and the dissolution that cause the deterioration of Portland cement concrete. The aluminum ions, which replace some of the silicon ions in the silicate lattice, create additional crosslinks between the silicate chains, producing a three-dimensional network that is stronger and more resistant to chemical attack than the two-dimensional chains that characterize the calcium silicate hydrate of Portland cement. The research of Jackson and her colleagues has also revealed that the mineral phases in Roman marine concrete are arranged in a specific microstructural pattern that contributes to the material's durability. The tobermerite crystals that form in the concrete over time are aligned along the surfaces of the voids and the pores in the material, creating a mineral lining that seals the pores and that prevents the penetration of water and dissolved salts into the interior of the concrete. This self-sealing behavior is analogous to the self-healing behavior that the Mazik team identified in land-based Roman concrete, and it represents another mechanism by which the Roman concrete actively maintains and improves its own integrity over time. The comparison between the nanostructure of Roman concrete and the nanostructure of Portland cement concrete has revealed a fundamental difference in the way the two materials respond to the passage of time. Portland cement concrete becomes more porous and more permeable over time as the calcium hydroxide is leached out and as the calcium silicate hydrel gradually degrades. Roman concrete becomes less porous and less permeable over time as the continued pozzolanic reaction fills the pores with new cementitious material and as the formation of tobermerite and phillipsite seals the remaining voids. The two materials, therefore, follow opposite trajectories of aging. Portland cement concrete degrades, while Roman concrete improves. The implications of this divergent aging behavior are profound. The infrastructure that is built with Portland cement concrete is an asset that depreciates over time, requiring increasing expenditure on maintenance and ultimately requiring replacement. The infrastructure that was built with Roman concrete is an asset that appreciates over time, becoming stronger and more durable with each passing century. The economic implications of this difference are enormous because the total cost of ownership of a structure built with Roman-style concrete would be far lower than the total cost of ownership of an equivalent structure built with Portland cement concrete, even if the initial construction cost of the Roman-style structure were higher. The discovery that Roman concrete actively improves with age has also raised questions about the theoretical limits of the material's durability. If the chemical reactions that strengthen the concrete continue indefinitely, as the evidence suggests they do, then the theoretical lifespan of Roman concrete is essentially unlimited, constrained only by the mechanical forces, the earthquakes, the floods, and the human interventions that might physically destroy the structure. The practical lifespan of the Pantheon, which has already exceeded 2,000 years with no sign of significant deterioration, may be measured not in centuries but in millennia, a prospect that is both inspiring and humbling. The environmental implications of a concrete that improves with age rather than deteriorating are equally significant. A structure that lasts for millennia rather than decades requires the production and the placement of concrete only once, rather than the multiple cycles of construction, deterioration, demolition, and reconstruction that characterize the life cycle of a structure built with Portland cement concrete. The total environmental impact of a single construction event, even if the construction uses a material that is somewhat more energy intensive to produce than Portland cement, is far less than the total environmental impact of the multiple construction events that are required to maintain the same function using a less durable material. The specific role of the mineral philipsite in the durability of Roman marine concrete has been elucidated by the research of Jackson and her colleagues. Philipsite is a zeolite mineral, a member of the same family of aluminosilicate minerals that are found in the volcanic ash from which the concrete was made. In the natural environment, philipsite forms in volcanic soils and in the alkaline waters of saline lakes, and its formation in Roman concrete is the result of the alkaline, mineral-rich chemical environment that exists within the pore spaces of the concrete. The formation of philipsite within the pores of the concrete serves several functions. First, it fills the pores, reducing the porosity and the permeability of the concrete, and thereby increasing its resistance to the penetration of water and dissolved salts. Second, the philipsite crystals interlock with each other and with the surrounding cementitious matrix, creating a denser and stronger material that is more resistant to mechanical failure. Third, the formation of philipsite is a continuous process that occurs over centuries, so that the concrete becomes progressively denser and stronger over time as more philipsite crystals form and fill the remaining pore spaces. The growth of philipsite and tobermarite in Roman concrete is an example of a phenomenon known as mineral paragenesis, the sequential formation of mineral phases in response to changing chemical conditions. In the case of Roman marine concrete, the initial pozzolanic reaction produces the calcium aluminum silicate hydrate gel that provides the early strength of the material. Over time, as seawater penetrates the pores of the concrete and interacts with the gel, the chemical conditions within the pores change, promoting the formation of new mineral phases, including tobermarite and philipsite, that fill the pores and strengthen the material. The mineral paragenesis in Roman concrete is therefore a self-sustaining process in which the interaction between the concrete and its environment drives the formation of minerals that improve the material's properties. The comparison between the mineral paragenesis in Roman concrete and the deterioration processes in Portland cement concrete reveals a fundamental difference in the way the two materials interact with their environments. In Portland cement concrete, the interaction with the environment is destructive. Water dissolves the calcium hydroxide, salts attack the cement minerals, and steel reinforcement corrodes. In Roman concrete, the interaction with the environment is constructive. Water promotes the formation of new minerals that strengthen the material. The two materials are therefore in fundamentally different relationships with their environments, one adversarial and one symbiotic, and this difference is the fundamental explanation for their divergent long-term performance. The concept of environmental symbiosis in construction materials, in which the material benefits from, rather than being harmed by its interaction with the environment, is one of the most important insights that the study of Roman concrete has provided. The development of modern construction materials that exhibit environmental symbiosis, materials that use the interaction with their environment to improve their properties rather than being degraded by it, is one of the most promising avenues of research in modern materials science, and the Roman concrete provides the most compelling historical model for this approach. The comparison between the carbon footprint of Roman concrete and the carbon footprint of Portland cement is one of the most compelling arguments for the adoption of Roman-inspired concrete in the modern world. The production of Portland cement requires the heating of limestone to approximately 1400 to 1500 degrees Celsius, a process that releases carbon dioxide both from the combustion of the fossil fuels that provide the heat and from the chemical decomposition of the limestone itself. The total carbon dioxide emissions from Portland cement production are approximately 800 kilograms per ton of cement, making the cement industry one of the largest industrial sources of greenhouse gas emissions in the world. The production of Roman-style concrete using volcanic ash and lime requires significantly less energy and produces significantly less carbon dioxide than the production of Portland cement concrete. The volcanic ash, which constitutes the bulk of the cementitious material in Roman concrete, requires no heating and generates no carbon dioxide emissions. The lime, which is produced by heating limestone to approximately 900 degrees Celsius, requires less energy than the production of Portland clinker and generates less carbon dioxide per unit of cementitious material. The total carbon dioxide emissions from the production of Roman-style concrete are estimated to be approximately 50 to 70% lower than the emissions from the production of an equivalent quantity of Portland cement concrete. The potential for reducing global carbon dioxide emissions through the adoption of Roman-inspired concrete is enormous. If the global concrete industry were to replace even a portion of its Portland cement usage with pozzolanic materials, the reduction in carbon dioxide emissions would be measured in hundreds of millions of tons per year, a reduction that would be significant in the context of the global effort to mitigate climate change. The adoption of pozzolanic cements and the development of new cementitious materials based on the principles of Roman concrete are therefore not merely academic exercises. They are practical measures that could make a meaningful contribution to the reduction of global greenhouse gas emissions. The economic incentive for reducing the carbon footprint of concrete production is growing as governments around the world implement carbon pricing mechanisms and emissions trading systems that impose a cost on carbon dioxide emissions. As the cost of carbon emissions increases, the economic advantage of low-carbon alternatives to Portland cement will increase as well, creating a market incentive for the adoption of pozzolanic cements and other low-carbon cementitious materials. The Roman concrete research, which has demonstrated that a low-carbon approach to concrete production can produce materials that are not merely equivalent to, but superior to Portland cement concrete in terms of durability, provides the scientific foundation for the development of these alternatives. The question of whether the modern world can afford to continue using Portland cement as its primary building material is one that the Roman concrete story forces us to confront. The financial cost of the deteriorating Portland cement infrastructure, the environmental cost of the carbon dioxide emissions from cement production, and the opportunity cost of building structures that last for decades rather than for centuries, all argue for a fundamental reconsideration of the modern approach to concrete construction. The Roman example demonstrates that a better approach is possible, an approach that produces more durable structures at a lower environmental cost, and the modern research on Roman concrete is providing the scientific knowledge that is needed to translate this possibility into practice. The role of the construction industry in the global response to climate change is a topic of increasing urgency, and the Roman concrete story provides a perspective on this topic that is both historical and practical. The historical perspective reminds us that a low-carbon approach to concrete production has been demonstrated to work over a timescale that is longer than the history of the modern construction industry itself. The practical perspective provides specific scientific insights and specific materials technologies that can be applied to the development of a more sustainable construction industry. The question of whether the construction industry will respond to the challenge of climate change by adopting the lessons of Roman concrete or by continuing with the current approach is one of the most important questions facing the industry and the world in the coming decades. The scientific evidence in favor of the Roman approach is strong, the potential economic benefits are enormous, and the environmental imperative is urgent. The question is whether the inertia of the industry, the conservatism of the regulatory framework, and the short-term economic incentives that favor the current approach will be overcome by the long-term advantages of the Roman-inspired alternative. The investigation of the specific conditions under which aluminum tobermorite forms in Roman concrete has been one of the most productive areas of the research. Tobermorite is a rare mineral in the natural environment, typically found in hydrothermal systems where hot, mineral-rich water interacts with calcium-rich rocks over long periods of time. The formation of tobermorite in Roman concrete at the ambient temperatures of the natural environment, without the high pressures and the elevated temperatures that are typically required for its formation, is one of the most surprising and most significant findings of the Roman concrete research. The mechanism by which tobermorite forms in Roman concrete at ambient temperatures has been elucidated through a combination of laboratory experiments and computational modeling. The research has shown that the specific chemical environment within the pores of Roman concrete, which is characterized by high alkalinity, high concentrations of dissolved calcium and aluminum, and the slow continuous supply of silica from the dissolving volcanic ash, provides the specific thermodynamic and kinetic conditions that are needed for the nucleation and the growth of tobermorite crystals. The formation of tobermorite is promoted by the presence of dissolved aluminum, which lowers the energy barrier for nucleation and which stabilizes the tobermorite structure once it has formed. The practical implications of the tobermorite formation mechanism are significant for the development of modern concrete materials. If the conditions that promote tobermorite formation in Roman concrete can be reproduced in modern concrete, it may be possible to produce a modern material that develops the same kind of long-term strengthening behavior that characterizes the Roman material. The key to reproducing these conditions is the selection of the appropriate pozzolanic material, one that provides the reactive silica and alumina that are needed for the pozzolanic reaction, and that creates the specific chemical environment within the pores that promotes the formation of tobermorite. The search for modern pozzolanic materials that can replicate the conditions for tobermorite formation is an active area of research. The volcanic ashes from various sources, the industrial byproducts such as fly ash and slag, and the synthetic pozzolanic materials that have been developed for specific applications are all being evaluated for their ability to promote the formation of tobermorite in concrete under ambient conditions. The results of these evaluations will determine which materials are most suitable for the production of modern concrete that exhibits the long-term strengthening behavior of the Roman original. The attempt to understand and to reproduce Roman concrete has been one of the most active and most productive areas of research in materials science over the past several decades. The research has drawn on expertise from a remarkable range of disciplines, including chemistry, geology, materials science, structural engineering, archaeology, and ancient history, and it has produced discoveries that have transformed our understanding of the material and that have significant practical implications for the modern construction industry. The first major line of investigation has been the chemical and mineralogical analysis of surviving Roman concrete samples. Researchers have obtained samples of Roman concrete from structures across the Mediterranean, including the Pantheon, the Colosseum, the markets of Trajan in Rome, the harbours at Caesarea and Portus Cassanus, and dozens of other Roman structures, and they have subjected these samples to the most advanced analytical techniques available to modern materials science. The analytical techniques that have been applied to Roman concrete include X-ray diffraction, which identifies the mineral phases present in the material, scanning electron microscopy, which produces high magnification images of the material's microstructure, energy dispersive X-ray spectroscopy, which determines the chemical composition of individual mineral grains, synchrotron X-ray microdiffraction, which provides detailed information about the crystal structure and the spatial distribution of mineral phases at the microscopic level, and Raman spectroscopy, which provides information about the molecular bonding within the material. These techniques have produced a comprehensive picture of the composition, the microstructure, and the mineral phases of Roman concrete that is far more detailed than anything that was available to earlier generations of researchers. The results of these analyses have revealed that Roman concrete is a complex material that contains a diverse assemblage of mineral phases, many of which are the products of the long-term chemical reactions between the original ingredients and the surrounding environment. The primary cementitious phase is a calcium aluminum silicate hydrate gel that is produced by the pozzolanic reaction between the volcanic ash and the lime. This gel, which is the primary source of the concrete strength, differs from the calcium silicate hydrate of Portland cement in its chemical composition, its crystal structure, and its stability in the presence of water. The gel is surrounded by and interspersed with a variety of other mineral phases, including zeolites, tobermorite, philipsite, and various calcium carbonate minerals, each of which contributes to the overall properties of the material. The second major line of investigation has been the experimental reproduction of Roman concrete using the ingredients and the techniques described by Vitruvius and by other ancient sources. Several research groups have attempted to produce Roman-style concrete by mixing lime, volcanic ash, and water in the proportions described by the ancient sources, and by curing the resulting material under conditions that approximate those of a Roman construction site. The results of these experimental reproductions have been instructive but mixed. The researchers have been able to produce concrete that is chemically similar to the Roman material, with a mineral assemblage that includes many of the same phases that have been identified in the ancient concrete. But the mechanical properties of the reproduced concrete have generally been inferior to those of the ancient material, particularly with respect to the long-term durability and the self-healing properties that are the most remarkable features of the Roman concrete. The gap between the reproduced and the original material suggests that there are aspects of the Roman production process that have not been fully understood or that have not been accurately reproduced in the modern experiments. The role of the volcanic ash in the performance of Roman concrete has been one of the most intensively studied aspects of the material. The volcanic ash that the Romans used, which came primarily from the volcanic deposits of Campania and from other volcanic sources around the Mediterranean, is not a uniform material. It varies in composition, in mineral content, and in physical properties from one deposit to another and from one layer within a deposit to another. The specific properties of the volcanic ash, including its content of reactive silica and alumina, its particle size distribution, and its mineral assemblage, influence the properties of the resulting concrete, and the selection of the appropriate volcanic ash was an important part of the Roman concrete maker's skill. The specific mineral content of the volcanic ash is particularly important. The volcanic deposits of Campania contain a family of minerals called zeolites, which are hydrated aluminosilicate minerals with an open, cage-like crystal structure that makes them highly reactive with lime and water. The zeolite content of the volcanic ash is one of the factors that distinguishes the Roman pozzolana from the less reactive volcanic materials that are found in other parts of the world, and it is one of the reasons why the concrete produced with Campanian pozzolana is superior to the concrete produced with volcanic materials from other sources. The role of seawater in the chemistry of Roman marine concrete has been another major area of investigation. The discovery that seawater promotes the formation of aluminum, tobermorite, and philipsite in Roman concrete, as reported by Marie Jackson and her colleagues, has opened a new avenue of research into the interactions between concrete and the marine environment. Jackson's work has shown that the dissolved salts in seawater, particularly the magnesium and the sulfate ions, react with the pozzolanic cement in the Roman concrete to produce mineral phases that strengthen the material rather than weakening it, a result that is exactly the opposite of what happens when modern Portland cement concrete is exposed to seawater. The numbers are striking when we compare the durability of Roman and modern marine concrete. A modern Portland cement concrete structure in a marine environment has an expected lifespan of approximately 50 years before significant deterioration occurs. A Roman marine concrete structure has survived for over 2,000 years in the same environment, and the analytical evidence suggests that it will continue to survive for thousands of years more. The ratio between the lifespans of the two materials is approximately 40:1, a difference that is extraordinary by any standard, and that underscores the fundamental superiority of to concrete construction in marine environments. The third major line of investigation has been the study of the lime component of Roman concrete, which has produced some of the most surprising and most consequential discoveries in the field. The traditional understanding of the lime component was that the Romans used slaked lime, calcium hydroxide, which was produced by slaking quicklime, calcium oxide, with water. The slaking process, which involves adding water to quicklime and allowing the resulting exothermic reaction to proceed to completion, produces a fine powder of calcium hydroxide that is then mixed with the volcanic ash and the aggregates to form the concrete. The Massic team's discovery, published in 2023, challenged this understanding by proposing that the Romans may have used a different technique for incorporating the lime into the concrete mix. Instead of using slaked lime, the Romans may have added quicklime, the unslaked calcium oxide, directly to the concrete mix, a technique known as hot mixing, because the exothermic reaction between the quicklime and the water generates significant heat. The hot mixing technique would explain the presence of the lime clasts in the Roman concrete, because the quicklime particles would not dissolve completely during the mixing process, leaving small fragments of unreacted calcium oxide that would subsequently hydrate, and that would serve as the reservoirs of calcium that enable the self-healing mechanism. The hot mixing hypothesis has been supported by experimental evidence. The Massic team produced concrete samples using both the traditional slaked lime technique and the hot mixing technique, and they found that the samples produced by hot mixing contained lime clasts that were similar in size, shape, and distribution to the lime clasts found in ancient Roman concrete. The team also found that the hot mix samples exhibited self-healing behavior when cracked and exposed to water, with the lime clasts dissolving and the released calcium reacting with the pozzolanic material to produce new cementitious compounds that filled the cracks. The discovery of the hot mixing technique has important practical implications for the modern construction industry. If the self-healing properties of Roman concrete can be reproduced using the hot mixing technique, it may be possible to produce modern concrete that is capable of repairing itself when cracks develop, reducing the need for maintenance and extending the lifespan of concrete structures. The potential economic benefits of self-healing concrete are enormous, given the trillions of dollars that are currently spent on the repair and the replacement of deteriorating concrete infrastructure around the world. The fourth major line of investigation has been the study of the structural engineering principles that the Romans used in their concrete construction. The Romans were not merely skilled at producing concrete, they were also skilled at using concrete in structural applications, designing and constructing buildings, bridges, aqueducts, and other structures that exploited the properties of concrete to achieve architectural forms that were impossible with other materials. The structural engineering of the Pantheon dome, which we have already described, is one of the most studied examples of Roman structural design. The research that has been conducted on the dome has revealed a level of engineering sophistication that is impressive by any standard, including the careful grading of the aggregate to reduce the weight of the dome, the use of step rings and coffers to distribute the structural loads, and the selection of concrete compositions that were optimized for the specific structural requirements of different parts of the dome. The study of Roman vaults and arches has revealed similar levels of engineering sophistication. The Romans developed a variety of vaulting techniques, including the barrel vault, the groin vault, and the cross vault, that exploited the compressive strength of concrete to create large, open interior spaces that would have been impossible to achieve with traditional post and lintel construction. The design of these vaults required an empirical understanding of the behavior of concrete under load, an understanding that the Romans acquired through centuries of construction experience, and that they transmitted through the apprenticeship system that trained the builders and the engineers of the Empire. The use of lightweight aggregates in the upper portions of the Pantheon dome is one of the most sophisticated examples of the Romans' structural use of concrete. The Romans understood empirically, if not theoretically, that the weight of the dome was a critical factor in its structural stability, and they reduced the weight of the upper portions by using pumice and other lightweight volcanic materials as aggregate. The result is a dome in which the density of the concrete varies from approximately 2,100 kilograms per cubic meter at the base to approximately 1,350 kilograms per cubic meter at the top, a variation that reduces the overall weight of the dome and that contributes to its structural stability. The comparison between the Pantheon dome and modern concrete structures is instructive. Modern reinforced concrete domes are typically thinner and lighter than the Pantheon dome, because the reinforcing steel provides tensile strength that the unreinforced Roman concrete lacks. But modern concrete domes are also less durable, because the reinforcing steel is vulnerable to corrosion, and because the Portland cement matrix is vulnerable to the chemical deterioration that we have described. The Pantheon dome, which contains no reinforcing steel and which is made of a material that is chemically self-healing, has outlasted every modern concrete structure and shows no signs of significant deterioration after nearly 2,000 years. The question of why Roman concrete was lost is one that connects to the broader story of the decline and fall of the Roman Empire, which we have discussed in other contexts. The collapse of the Western Roman Empire in the 5th century was accompanied by the loss of the institutional infrastructure, the supply chains, the training systems, and the engineering traditions that had sustained the Roman construction enterprise. The volcanic ash from Campania, which was the key ingredient of Roman concrete, was no longer available to builders in other parts of the former empire because the trade networks that had distributed it had collapsed. The engineers and the builders who knew how to select, to mix, to place, and to cure the concrete were no longer trained because the apprenticeship systems that had transmitted the knowledge had been disrupted, and the large-scale construction projects that had provided the demand for concrete, the harbours, the aqueducts, the public buildings, were no longer being undertaken because the political and economic structures that had funded them no longer existed. The loss of Roman concrete was therefore not a single event, but a gradual process, parallel to the broader decline of Roman civilization. The knowledge was not destroyed in a catastrophe. It was eroded, piece by piece, as the conditions that had sustained it were progressively removed. The volcanic ash was no longer shipped. The engineers were no longer trained. The projects were no longer funded. And the concrete that had built an empire was forgotten, its recipe lost in the general collapse of the knowledge systems that had sustained the Roman world. The archaeological study of Roman concrete has been an essential complement to the laboratory analysis of the material, providing information about the specific construction techniques, the specific materials, and the specific structural designs that the Romans used in their concrete buildings. The archaeological investigation of Roman construction sites has revealed the formwork systems that were used to shape the concrete, the tools that were used to mix and to place the material, and the construction sequences that were followed in the building of specific structures. The formwork systems that the Romans used were typically made of wood, and they included both reusable forms, which were disassembled after the concrete had hardened and used again for subsequent pours, and permanent forms, which were left in place as part of the finished structure. The design of the formwork was a critical aspect of the construction process, because the formwork determined the shape and the surface finish of the finished concrete, and the engineering of the formwork for large and complex structures, such as domes and vaults, required sophisticated carpentry skills and a detailed understanding of the geometry of the structure. The construction sequences that were used for major Roman concrete structures have been reconstructed through the analysis of the concrete itself, which preserves a record of the order in which the material was placed. The layers of concrete that are visible in cross-sections of Roman structures, known as construction joints, mark the boundaries between successive pours and provide information about the pace and the organization of the construction process. The analysis of construction joints has revealed that the Roman builders typically placed concrete in horizontal layers of approximately 60 to 90 centimeters in thickness, allowing each layer to begin to harden before the next layer was placed on top of it. The Roman technique of placing concrete in layers, rather than in a single continuous pour, has been identified by researchers as an important factor in the quality and the durability of the finished material. The layered placement allowed each layer to develop initial strength before it was loaded by the weight of the subsequent layers, reducing the risk of bendiformation or collapse during construction. The layered technique also promoted the development of a more uniform microstructure because each layer was exposed to the air and to moisture during the interval between pours, allowing the pozzolanic reaction to proceed more evenly throughout the material. The study of the aggregate distribution within Roman concrete has revealed additional information about the construction techniques that were used. The aggregate in Roman concrete is not randomly distributed. It is carefully graded, with larger pieces of aggregate placed at the bottom of each layer and smaller pieces placed at the top. This grading, which was probably achieved by the Roman builders through careful placement of the aggregate rather than through mechanical sorting, improved the structural performance of the concrete by concentrating the denser, heavier aggregate where the structural loads were greatest. The investigation of Roman concrete from different periods of the empire's history has revealed a pattern of technological evolution in which the quality and the sophistication of the concrete improved over time. The earliest Roman concrete, from the 3rd and 2nd centuries before the Common Era, was a relatively crude material that was used primarily for fill and for foundations. The concrete of the late Republic and the early Empire, from the 1st century before the Common Era to the 2nd century of the Common Era, was a more refined material that was used for vaults, domes, and other structurally demanding applications. The concrete of the later Empire, from the 3rd to the 5th century, incorporated innovations in the composition of the mix and in the techniques of placement that reflected the accumulated experience of several centuries of construction practice. The modern applications of the principles of Roman concrete are being actively pursued by research groups and companies around the world. The most direct application is the development of concrete mixes that incorporate pozzolanic materials, such as volcanic ash, fly ash, or ground granulated blast furnace slag, as partial replacements for Portland cement. These supplementary cementitious materials produce concrete that is more durable, more resistant to chemical attack, and less energy intensive to produce than conventional Portland cement concrete. The use of fly ash, which is a byproduct of coal combustion in power plants, and which has pozzolanic properties similar to those of volcanic ash, is the most widely used supplementary cementitious material in modern concrete. Fly ash concrete is widely used in the construction of bridges, highways, and other infrastructure, and its use has been shown to improve the long-term durability of the concrete and to reduce the carbon emissions associated with cement production. The similarity between fly ash and the volcanic ash used by the Romans has been noted by several researchers who have pointed out that the Romans inadvertently pioneered the use of pozzolanic materials in concrete, a practice that the modern industry has adopted for both environmental and performance reasons. The development of geopolymer cements, which are cementitious materials that are produced entirely from pozzolanic reactions without the use of Portland cement, is another area of research that has been inspired by the Roman example. Geopolymer cements use industrial byproducts such as fly ash or slag that are activated by alkaline solutions to produce cementitious gels that are chemically similar to the gels produced by the pozzolanic reaction in Roman concrete. Geopolymer cements produce concrete that is highly durable, resistant to chemical attack, and virtually carbon-free in its production, making them one of the most promising alternatives to Portland cement for sustainable construction. The development of self-healing concrete, inspired by the lime-clast mechanism discovered in Roman concrete, is being pursued by several research groups. The Masick team at MIT has demonstrated that modern concrete incorporating limeclasts can exhibit self-healing behavior similar to that observed in Roman concrete, and they are working to develop commercial applications of this technology. Other groups are developing self-healing concrete using different mechanisms, including the encapsulation of healing agents in microcapsules that rupture when cracks form, and the use of bacteria that produce calcium carbonate when activated by water penetrating the cracks. The variety of approaches to self-healing concrete reflects the intensity of interest in this area, and the recognition that self-healing is one of the most desirable properties that concrete can possess. The potential for carbon capture and storage in concrete is another area of research that is connected to the Roman concrete story. Some researchers have proposed that concrete could be used as a medium for the permanent storage of carbon dioxide by incorporating carbon dioxide into the concrete mix or by exposing the concrete to carbon dioxide during the curing process. The Roman concrete, which continues to react with carbon dioxide and water over millennia, provides a natural model for the long-term storage of carbon in cementitious materials, and the understanding of the long-term chemistry of Roman concrete could inform the development of carbon storage concrete for modern applications. The development of Roman concrete technology did not occur in isolation. It was part of a broader tradition of construction innovation that encompassed not only the materials of construction, but also the structural forms, the construction techniques, and the organizational systems that were used to realize the ambitious building programs of the Roman state. The evolution of Roman architecture from the simple stone and brick structures of the early Republic to the monumental concrete buildings of the empire was a process of innovation that occurred over a period of several centuries, and that involved the contributions of countless engineers, architects, builders, and laborers. The Roman invention of the arch, the vault, and the dome as primary structural forms was directly connected to the development of concrete as a building material. The arch, which concentrates the weight of a structure along a curved line that follows the natural flow of compressive forces, was used by pre-Roman civilizations, but the Romans were the first to exploit the arch systematically as a structural element in large-scale construction. The vault, which is essentially an arch extended in the third dimension, allowed the Romans to create large, covered interior spaces that were impossible to achieve with the post and lintel construction that characterized earlier building traditions. And the dome, which is the ultimate expression of the arch principle, allowed the Romans to create circular, covered spaces of unprecedented scale, the most famous of which is the Dome of the Pantheon. The connection between the development of concrete and the development of these structural forms was synergistic. Concrete was the ideal material for the construction of arches, vaults, and domes, because it could be poured into formwork of any shape, and because it developed strength as a monolithic mass without the joints and the interfaces that weakened structures built of cut stone or brick. The availability of concrete, in turn, encouraged the Roman architects and engineers to experiment with new structural forms that exploited the material's properties, leading to the development of the barrel vault, the groin vault, the cross vault, and the dome as standard elements of Roman architecture. The Colosseum, which was built between 70 and 80 of the Common Era, and which is one of the most iconic structures of the Roman world, provides an impressive example of the integration of concrete construction with advanced structural engineering. The Colosseum structure consists of a series of radial and concentric arches and vaults, constructed of concrete and faced with travertine stone, that distribute the weight of the structure and the loads imposed by the spectators across the entire circumference of the building. The structural system of the Colosseum is a masterpiece of engineering that demonstrates the Romans' sophisticated understanding of the behavior of concrete under complex loading conditions. The markets of Trajan, built in the early 2nd century of the Common Era, represent another milestone in the development of Roman concrete construction. The markets, which consist of a complex of multi-story buildings arranged on a hillside overlooking the Forum of Trajan, feature concrete vaults and walls that are among the best preserved examples of Roman concrete construction. The concrete of the markets of Trajan has been extensively studied by researchers, and the results have confirmed that the material is of exceptional quality, with a well-developed pozzolanic microstructure and a density that indicates thorough consolidation and careful curing. The study of Roman concrete has benefited from the development of new analytical techniques that have allowed researchers to examine the material at scales and with a precision that were not possible using earlier methods. The application of synchrotron X-ray techniques, which use the intense, finely focused X-ray beams produced by particle accelerators to probe the structure of materials at the atomic level, has been particularly productive. The synchrotron studies conducted by Marie Jackson and her collaborators at the Advanced Light Source at Lawrence Berkeley National Laboratory have produced some of the most detailed and most informative data on the mineral phases and the microstructure of Roman concrete, revealing features that were invisible to conventional X-ray and electron microscopy techniques. The application of neutron diffraction, another advanced analytical technique that uses beams of neutrons to probe the crystal structure of materials, has provided complementary information about the phases and the microstructure of Roman concrete. Neutron diffraction is particularly useful for studying materials that contain hydrogen, because neutrons interact strongly with hydrogen atoms, making it possible to identify and to characterize the hydrated mineral phases that are the primary cementitious components of the concrete. The combination of synchrotron X-ray techniques and neutron diffraction has provided a comprehensive picture of the mineral phases, the crystal structures, and the spatial relationships that characterize Roman concrete at the microscopic and the nanoscopic scales. The use of Raman spectroscopy, which measures the vibrational frequencies of the chemical bonds in a material, has provided additional information about the molecular structure of the cementitious phases in Roman concrete. Raman spectroscopy is particularly useful for identifying and characterizing the different forms of calcium silicate hydrate and calcium aluminum silicate hydrate that are present in the concrete, and it has been used to confirm the presence of aluminum tobermorite and philipsite in the marine concrete samples studied by Jackson and her colleagues. The computational modeling of the chemical reactions that occur during the production and the aging of Roman concrete has been another important tool for understanding the material. The computational models, which simulate the thermodynamic and kinetic processes that govern the formation and the transformation of the mineral phases in the concrete, have been used to predict the conditions under which tobermorite and philipsite form, to estimate the rates of the pozzolanic reactions, and to evaluate the long-term stability of the cementitious phases. These models have confirmed the experimental findings and have provided a theoretical framework for understanding the chemical processes that give Roman concrete its extraordinary durability. The integration of analytical data, computational modeling, and experimental reconstruction has produced a comprehensive understanding of Roman concrete that is far more detailed and far more complete than anything that was available even a decade ago. The progress that has been made in recent years has been extraordinary, and the rate of new discoveries shows no sign of diminishing. The study of Roman concrete remains one of the most active and most productive areas of research in materials science, and the results of this research are being applied to the development of new concrete materials that incorporate the principles of the Roman approach, while meeting the requirements of modern construction. The field testing of modern concrete mixes that incorporate Roman-inspired ingredients and techniques is an important next step in the translation of laboratory research into practical application. Several pilot projects have been initiated in which concrete mixes containing volcanic ash, fly ash, or other pozzolanic materials are being used in real-world construction applications and monitored over time to assess their long-term performance. These pilot projects, which will provide data on the durability and the maintenance requirements of the new materials under actual service conditions, are essential for building the confidence of the construction industry in the viability of Roman-inspired concrete as an alternative to conventional Portland cement concrete. The standardization and the codification of Roman-inspired concrete mixes in the building codes and the construction specifications of the modern world is the final step in the adoption of these materials by the construction industry. The development of standards for pozzolanic cements, for volcanic ash aggregates, and for self-healing concrete mixes is an ongoing process that involves the collaboration of researchers, engineers, standards organizations, and regulatory authorities. The adoption of these standards will provide the legal and the regulatory framework that is needed for the widespread use of Roman-inspired concrete in modern construction, and it will mark the completion of a cycle that began with the loss of the Roman recipe 1500 years ago, and that will end with its rediscovery and its adaptation to the needs of the modern world. The study of the specific volcanic ash deposits that the Romans used for their concrete has been an important aspect of the archaeological and geological investigation of the material. The volcanic deposits of the Phlegrean Fields, the area around Pozzuoli, that is the type locality for pozzolana, have been extensively studied, and the specific layers within these deposits that were preferred by the Roman builders have been identified. The preferred layers are those that have the highest content of reactive minerals, including zeolites and glassy volcanic fragments, and that have the finest particle size, characteristics that maximize the reactivity of the ash with lime and water. The volcanic deposits of the area around Rome itself, which include the tuffo deposits that underlie much of the city and its surrounding region, were also used extensively in Roman concrete production. The tuffo, which is a consolidated volcanic ash that can be quarried as a building stone and also ground into a fine powder for use as a pozzolanic additive, was the most readily available volcanic material in the immediate vicinity of Rome, and it was used in large quantities for concrete construction throughout the city and its surroundings. The volcanic ash from the island of Santorini, which is the remnant of one of the most powerful volcanic eruptions in recorded history, the Minoan eruption of approximately 1600 before the Common Era, was particularly valued by the Romans for marine concrete construction. The Santorini ash, which has specific chemical and mineralogical properties that make it particularly effective as a pozzolanic additive in marine environments, was transported across the eastern Mediterranean by ship and was used in the construction of harbours and other marine structures in the Greek-speaking eastern portion of the Roman Empire. The transport of volcanic ash from distant sources to construction sites across the empire required the organization of a supply chain that was one of the most impressive logistical achievements of the Roman world. The ash had to be quarried or collected from the volcanic deposits, loaded onto ships or carts, transported across distances of hundreds or thousands of kilometers, unloaded at the construction site, stored until it was needed, and then mixed with lime and water to produce the concrete. The efficiency of this supply chain, which was able to deliver volcanic ash in quantities sufficient for the largest construction projects in the history of the ancient world, is a testament to the organizational capabilities of the Roman state and to the sophistication of the Roman commercial and transportation networks. The decline of this supply chain during the fall of the Western Roman Empire was one of the primary factors in the loss of the Roman concrete tradition. When the political and economic structures that had organized the trade in volcanic ash collapsed, the builders of the successor states in Western Europe were cut off from the specific raw material that was essential for the production of high-quality concrete. The local volcanic materials that were available in some parts of Europe were sometimes used as substitutes, but they generally lacked the specific properties that made the Campanian and Santorini ashes so effective, and the resulting concrete was of lower quality than the Roman original. The role of water in the chemistry of Roman concrete deserves more detailed examination, because water plays a fundamentally different role in Roman concrete than it does in Portland cement concrete. In Portland cement concrete, water is primarily a reactant in the hydration reactions that produce the strength of the material, and the amount of water used in the mix is a critical variable that must be carefully controlled. Excess water which does not participate in the hydration reactions, remains in the concrete as free water that occupies pore spaces, and that contributes to the porosity and the permeability of the material. The presence of free water in Portland cement concrete is one of the factors that contributes to its vulnerability to deterioration, because the free water provides a medium through which dissolved salts and other harmful substances can penetrate the interior of the concrete. In Roman concrete, water plays a different role. The pozzolanic reaction, which is the primary cementitious reaction in Roman concrete, is slower than the hydration of Portland cement, and it continues over much longer periods of time. The water that is present in the concrete is not merely a reactant that is consumed in the initial setting process. It is as an ongoing participant in the chemical processes that strengthen and densify the material over time. The water that permeates the pores of the concrete carries dissolved ions that react with the cementitious matrix to produce new mineral phases, including tabermarite and philipsite, that fill the pores and that increase the strength and the durability of the material. The interaction between water and the lime clasts in Roman concrete is particularly important because it is this interaction that enables the self-healing mechanism. When a crack forms in the concrete and water enters the crack, the water dissolves the calcium oxide in the nearby lime clasts, releasing calcium ions into solution. The dissolved calcium reacts with the pozzolanic material in the surrounding concrete to produce new calcium aluminum silicate hydrate gel that fills the crack and restores the structural integrity of the material. The self-healing process is therefore dependent on the presence of water, which serves as both the medium through which the healing reaction occurs and the trigger that initiates the reaction by dissolving the lime clasts. The relationship between water and the long-term performance of Roman concrete is therefore symbiotic. The concrete uses water as a resource for self-improvement rather than suffering it as an agent of destruction. This symbiotic relationship is one of the most remarkable and most distinctive features of Roman concrete, and it represents a fundamentally different approach to the management of water in cementitious materials than the approach that characterizes Portland cement concrete. The implications of this symbiotic relationship for the design of modern concrete are significant. The conventional approach to managing water in Portland cement concrete is to minimize the water content of the mix and to protect the finished concrete from the ingress of water using waterproofing membranes, sealants, and other protective measures. The Roman approach suggests an alternative strategy, designing the concrete so that the interaction with water improves the material rather than damaging it. This alternative strategy, which would reduce or eliminate the need for waterproofing, and which would allow the concrete to benefit from exposure to water rather than being harmed by it, could fundamentally change the design and the maintenance of concrete structures. The study of the interaction between Roman concrete and different types of water, including freshwater, seawater, and water containing various dissolved minerals, has revealed that the specific mineral phases that form in the concrete depend on the specific composition of the water. The formation of tabermarite and philipsite, which are the strengthening minerals that have been identified in Roman marine concrete, is promoted by the specific ions that are present in seawater, particularly magnesium, sulfate, and chloride. The formation of different mineral phases in freshwater environments suggests that the long-term performance of Roman concrete may vary depending on the specific aqueous environment in which the concrete is placed. An important consideration for the modern application of Roman concrete principles to different types of construction. The study of the kinetics of the pozzolanic reaction, the rate at which the reaction proceeds under different conditions, has provided additional information about the factors that control the long-term performance of Roman concrete. The rate of the pozzolanic reaction depends on the temperature, the availability of water, the surface area of the pozzolanic particles, and the alkalinity of the pore solution. The rate increases with increasing temperature and with increasing alkalinity, and it decreases as the surface area of the pozzolanic particles is consumed by the reaction. The slow rate of the pozzolanic reaction at ambient temperatures is one of the reasons why Roman concrete continues to strengthen over centuries, because the reaction proceeds at a rate that is too slow to be completed during the initial curing period, but that is fast enough to produce significant strengthening over decades and centuries. The question of how the Roman concrete tradition influenced the subsequent development of construction technology in the Mediterranean region and beyond is one that connects the Roman story to the broader history of building materials. The Byzantine builders, who inherited the Roman construction tradition, continued to use pozzolanic concrete in their buildings, though the quality of the Byzantine concrete was generally lower than the best Roman examples. The Hagia Sophia in Constantinople, which was built in the 6th century of the Common Era, and which features one of the largest domes in the world, used a concrete that was derived from the Roman tradition, but that incorporated modifications that reflected the specific materials and the specific techniques that were available to the Byzantine builders. The Islamic builders who succeeded the Byzantines in many parts of the Mediterranean world also used lime-based mortars and concretes in their construction, and some Islamic buildings exhibit properties that suggest the use of pozzolanic materials. The great mosques, palaces, and fortifications of the Islamic world demonstrate a mastery of construction technology that was in many respects comparable to the Roman achievement, and the question of the extent to which the Islamic tradition drew on the Roman precedent is one that has been explored by historians of technology and architecture. The medieval European revival of interest in lime-based construction, which occurred in the 12th and 13th centuries, produced the great Gothic cathedrals and other monumental stone buildings that are among the most impressive architectural achievements of the medieval period. The medieval builders used lime mortars rather than pozzolanic concrete for most of their construction, and the structural principles of Gothic architecture, which relied on the compression of stone arches and vaults rather than on the monolithic strength of concrete, were fundamentally different from the structural principles of Roman concrete construction. The medieval European tradition, while it produced buildings of extraordinary beauty and structural ingenuity, did not recover the specific technology of pozzolanic concrete that the Romans had developed. The rediscovery of hydraulic cement in the 18th century by John Smeaton, who used a hydraulic lime to construct the third Eddystone lighthouse off the coast of England in 1756, marked the beginning of the modern era of cement technology. Smeaton discovered that lime produced from limestone containing clay developed hydraulic properties, setting and hardening in the presence of water, a discovery that led directly to the development of Portland cement by Aspin in the following century. Smeaton's work, while it was not directly influenced by the Roman tradition, produced a material that addressed the same problem that the Roman pozzolanic concrete had solved: the need for a cementitious material that could set and harden underwater. The relationship between Smeaton's hydraulic cement and the Roman pozzolanic concrete is one of convergent innovation. Two different approaches to the same problem, developed independently and separated by over a millennium, that arrived at different solutions with different long-term performance characteristics. The Roman solution, which used volcanic ash as the primary pozzolanic additive, produced a material with superior long-term durability. The modern solution, which uses the inherent pozzolanic properties of fired clay in the cement itself, produces a material that is faster to set and easier to produce at scale, but that is less durable in the long term. Everything we have discussed so far concerns the specific chemistry of Roman concrete, the specific minerals that give it its extraordinary durability, and the specific scientific discoveries that have begun to explain how a material produced by ancient builders could outperform the products of modern materials science. These are important matters, and the ongoing research on Roman concrete continues to produce results of great scientific and practical significance. But beneath these specifics lies a deeper truth, a truth that concerns not just what Roman concrete was, but what its loss and its rediscovery tell us about the nature of technological knowledge. the relationship between empirical craft and theoretical science, and the paradox of a modern civilization that cannot match the durability of an ancient one. The deeper truth is this: the Romans solved a problem that we have not solved. They produced a building material that was durable, self-healing, and environmentally superior to the material that we use today, and they did it without any understanding of the chemistry that made their material work. They did not know about calcium silicate hydrate. They did not know about pozzolanic reactions. They did not know about aluminum tobermarite, or philipsite, or carbon segregation, or any of the other chemical processes that modern science has identified as the keys to the performance of their concrete. They simply mixed their ingredients, poured their concrete, and built structures that have lasted for 2,000 years. This is not science fiction. This is a fact that should humble every material scientist and every civil engineer in the modern world. The Romans, working with the simplest of tools and the most rudimentary understanding of chemistry, produced a material that is, in at least one critical respect, superior to the material that the most advanced industrial civilization in human history produces, using the most sophisticated technology and the most complete scientific understanding available. The superiority of Roman concrete in terms of durability is not a matter of dispute. It is a matter of measurement, of observation, of physical evidence that is visible in every surviving Roman structure, and that is confirmed by every scientific analysis of the ancient material. Something is wrong with our approach to concrete production. The modern concrete industry, which is one of the largest and most important industries in the world, produces a material that begins to deteriorate almost immediately after it is poured, that requires expensive and disruptive maintenance throughout its lifespan, and that must be completely replaced after a few decades. The Roman approach, which used different ingredients and different techniques, produced a material that improves over time, that heals itself when it is damaged, and that has lasted for millennia without significant maintenance. The comparison between the two approaches is not flattering to the modern one, and it raises fundamental questions about whether the modern concrete industry has optimized for the wrong variables. The modern concrete industry has optimized for speed, for cost, and for consistency. Portland cement concrete can be mixed, poured, and cured quickly. It can be produced inexpensively, using raw materials that are widely available and using processes that are highly standardized and easily scalable. And it can be produced with consistent properties, meeting precise specifications for strength, workability, and other performance criteria. These are real and important advantages, and they explain why Portland cement concrete has become the dominant building material of the modern world. But the optimization for speed, cost, and consistency has come at the expense of durability, and the consequences of this trade-off are becoming increasingly apparent. The infrastructure of the modern world is deteriorating at a rate that is unsustainable, and the cost of repairing and replacing the deteriorating concrete structures is consuming an ever-increasing share of public resources. The environmental cost of concrete production, which is responsible for approximately 8% of global carbon dioxide emissions, is also unsustainable, and the contribution of the concrete industry to climate change is a problem that will only grow as the developing world continues to urbanize and to build. The Roman approach offers an alternative that addresses both the durability problem and the environmental problem simultaneously. Roman-style concrete, which uses volcanic ash instead of Portland cement as its primary cementitious material, requires less energy to produce, generates less carbon dioxide, and produces a material that is far more durable than Portland cement concrete. The adoption of Roman-inspired concrete recipes could therefore reduce both the financial and the environmental costs of concrete construction while producing structures that last for centuries rather than decades. Let that sink in. We have been building with an inferior material for 200 years, when a superior alternative was available, or at least knowable, for 2000. The recipe was lost, not because it was secret, as the recipe for Greek fire was secret, but because the civilization that used it collapsed and the institutional infrastructure that sustained the knowledge was destroyed. The recipe was not hidden, it was forgotten, and the forgetting has cost us trillions of dollars in infrastructure maintenance, billions of tons of unnecessary carbon dioxide emissions, and countless hours of disruption and inconvenience as our crumbling concrete is patched and repaired and ultimately replaced. The rediscovery of the principles of Roman concrete is one of the most important developments in modern materials science, not because it provides a ready-made solution to the modern concrete problem, but because it demonstrates that a fundamentally different approach to concrete production is possible, and that the approach can produce results that are superior to those achieved by the current approach. The specific recipe of Roman concrete may not be directly applicable to modern construction because the specific volcanic ash that the Romans used is not available in the quantities that modern construction would require, and because the specific techniques of mixing, placing, and curing that the Romans used are not compatible with the speed and the scale of modern construction practices. But the principles that the Roman recipe embodies, the use of pozzolanic reactions rather than Portland cement hydration, the incorporation of self-healing mechanisms, the optimization for long-term durability rather than short-term strength, are principles that can be adapted and applied to modern concrete production. The development of modern pozzolanic cements, which incorporate volcanic ash, fly ash, ground granulated blast furnace slag, or other pozzolanic materials into the concrete mix, is one practical application of the principles of Roman concrete. These modern pozzolanic cements produce concrete that is more durable, more resistant to chemical attack, and less energy intensive to produce than conventional Portland cement concrete. The use of supplementary cementitious materials, as these pozzolanic additives are called, has been increasing in recent decades, driven by both the desire for improved durability and the need to reduce the carbon emissions associated with cement production. The development of self-healing concrete, which incorporates mechanisms that allow the concrete to repair cracks and voids without human intervention, is another area of modern research that has been inspired by the Roman example. The Massic team's discovery of the lime-classed self-healing mechanism in Roman concrete has provided a specific model for the design of modern self-healing concrete, and several research groups are now working to develop commercial products that incorporate this or similar self-healing mechanisms. The broader implications of the Roman concrete story for the philosophy of science and technology are worth considering. The story demonstrates that empirical knowledge, the knowledge that is acquired through observation, experimentation, and practical experience, can sometimes produce results that are superior to those produced by theoretical knowledge, the knowledge that is derived from scientific analysis and mathematical modeling. The Romans, who had no theoretical understanding of the chemistry of their concrete, produced a material that modern scientists, who have a comprehensive theoretical understanding of the chemistry of concrete, have been unable to match. The gap between the Roman achievement and the modern one is not a gap in theoretical knowledge. It is a gap in practical knowledge, in the empirical understanding of materials that comes from centuries of hands-on experience with specific ingredients and specific techniques. The concept of lost optimization is useful for understanding this gap. The Romans, through centuries of trial and error, had optimized their concrete recipe for durability, arriving at a combination of ingredients and techniques that produced the best possible result for their specific purpose. This optimization was achieved empirically, without any theoretical framework to guide it, and the specific values of the optimized variables, the specific ash, the specific lime, the specific mixing technique, the specific curing conditions, were encoded in the practical knowledge of the concrete makers, rather than in any written document. When the practical knowledge was lost, the optimization was lost with it, and the modern researchers who are attempting to reproduce the Roman material are, in effect, trying to rediscover an optimization that took the Romans centuries to achieve. The modern scientific approach to the Roman concrete problem is to analyze the ancient material, to identify the specific features that give it its remarkable properties, and to develop modern recipes and techniques that reproduce those features. This approach has been productive, and it has produced important advances in the understanding of Roman concrete and in the development of more durable modern alternatives. But the approach has also highlighted the limitations of scientific analysis as a substitute for practical experience. The analysis can identify what the Roman concrete contains and what chemical processes are responsible for its properties, but it cannot, by itself, specify the exact recipe and the exact technique that will produce a material with the same properties, because the relationships between the variables, the ingredients, the proportions, the mixing method, the curing conditions are too complex to be determined by analysis alone. The rediscovery of Roman concrete is therefore not merely a matter of chemical analysis. It is a matter of re-optimization, of repeating the process of trial and error that the Romans went through over centuries, but with the advantage of the scientific understanding that the analysis has provided. The modern researchers who are attempting to reproduce Roman concrete are combining the empirical approach of the ancient builders with the analytical tools of modern science, using the scientific understanding to guide the experimentation and using the experimentation to validate the scientific understanding. This combination of approaches, which represents the best of both the ancient and the modern traditions, is the most promising path toward the rediscovery of a material that the Romans knew how to make, and that we are only now beginning to learn how to make again. The philosophical dimension of the Roman concrete story extends to the question of what we mean by progress in the context of materials technology. The standard narrative of technological progress, which presents the history of technology as a continuous advance from primitive to sophisticated, from natural to synthetic, from handmade to machine-made, is challenged by the Roman concrete story in a fundamental way. The narrative assumes that modern materials are always superior to ancient materials, that the products of industrial chemistry are always better than the products of empirical craftsmanship, and that the direction of technological change is always forward. The Roman concrete story demonstrates that none of these assumptions is universally true. The concept of appropriate technology, which emphasizes the importance of matching technological solutions to specific environmental and social conditions, rather than pursuing the most advanced or the most sophisticated technology available, is relevant to the Roman concrete discussion. The Roman concrete recipe was an appropriate technology for the specific conditions of the Roman world. It used locally available materials. It could be produced using simple tools and techniques. It was suitable for the specific construction challenges that the Romans faced, and it produced results that were well adapted to the environmental conditions of the Mediterranean region. The modern Portland cement recipe, by contrast, is a universal technology that is designed to be applicable in any environment and under any conditions, but that is optimized for none. The tension between appropriate and universal technology is one of the central tensions in the modern construction industry. The universal approach, which uses a single material, Portland cement concrete, for virtually all construction applications, has the advantage of simplicity and consistency, but it has the disadvantage of suboptimal performance in specific environments and specific applications. The appropriate approach, which uses materials that are specifically adapted to the conditions of each construction project, has the advantage of optimized performance, but it has the disadvantage of complexity and variability. The Roman concrete story suggests that the appropriate approach can produce results that are dramatically superior to the universal approach, at least in some applications, and that the modern industry's reliance on a single universal material may not be the best strategy for long-term performance. The question of why the modern construction industry has been so slow to adopt the lessons of Roman concrete is worth considering. The scientific discoveries that have revealed the superior durability of Roman concrete and the mechanisms that produce it have been published in leading scientific journals and have received widespread media attention. The potential economic and environmental benefits of adopting Roman-inspired concrete recipes have been documented by multiple research groups. And yet, the modern construction industry continues to rely primarily on Portland cement concrete, and the adoption of pozzolanic cements and self-healing concrete has been slow. The answer lies in part in the inertia of the modern construction industry, which is one of the most conservative industries in the world. The industry standards, specifications, and building codes are based on Portland cement concrete, and the adoption of new materials requires changes in standards, in specifications, in testing procedures, and in construction practices that are difficult and time-consuming to implement. The industry's supply chains are optimized for Portland cement production, and the development of alternative supply chains for pozzolanic materials and for the new ingredients that would be needed for Roman-inspired concrete would require significant investment and organizational change. The answer also lies in the different time horizons that characterize the modern and the Roman approaches to construction. The modern construction industry operates on a short time horizon, typically 10 to 30 years, which is the period over which the economic return on a construction investment is calculated. Within this time horizon, Portland cement concrete performs adequately, and the additional cost of a more durable material is difficult to justify on economic grounds. The Roman construction enterprise operated on a much longer time horizon, building structures that were intended to last for centuries, and the additional investment in more durable materials was justified by the longer period over which the benefits would be realized. The mismatch between the short-term economic incentives of the modern construction industry and the long-term benefits of more durable construction is one of the most important obstacles to the adoption of Roman-inspired concrete. The resolution of this mismatch will require changes in the way construction projects are financed and evaluated, changes that take into account the long-term costs of maintenance and replacement, as well as the short-term costs of construction. The concept of life cycle costing, which evaluates the total cost of a structure over its entire lifespan, rather than just the cost of initial construction, provides a framework for this kind of long-term thinking. And the adoption of life cycle costing as a standard practice in the construction industry could create the economic incentive for the use of more durable materials. The comparison between the Roman and the modern approaches to construction provides a powerful illustration of the concept of temporal discounting, the tendency of individuals and organizations to value immediate benefits more highly than future benefits. The modern construction industry, which operates within a short-term economic framework, values the immediate benefits of low construction costs and fast completion times more highly than the long-term benefits of durability and reduced maintenance costs. The Roman construction enterprise, which operated within a longer-term political and cultural framework, valued the long-term benefits of durability and permanence more highly than the short-term benefits of speed and cost reduction. The concept of temporal discounting is well established in economics and in psychology, and it provides a powerful explanation for many of the decisions that individuals and organizations make about investment and consumption. The tendency to discount future benefits in favor of immediate ones is a fundamental feature of human decision-making, and it explains why individuals often choose to consume rather than to save, why companies often choose short-term profits over long-term investment, and why governments often choose to defer maintenance and infrastructure investment in favor of more immediately visible expenditures. The Roman approach to construction, which valued durability and permanence, was supported by a political and cultural framework that counteracted the natural tendency toward temporal discounting. The Roman emperors, who funded the most ambitious construction projects, were motivated not only by practical considerations, but also by the desire to create monuments that would perpetuate their names and their legacies for future generations. The cultural value that the Romans placed on permanence and durability created an incentive for investment in high-quality construction that was not diminished by the natural tendency to discount future benefits. The modern world lacks a comparable incentive structure. the economic framework within which modern construction operates values speed and cost reduction above all other considerations, and the political framework rewards investments that produce visible results within the short time horizons of electoral cycles. The result is a construction industry that is optimized for the short term, producing structures that are cheap and fast to build, but that deteriorate rapidly, and that impose enormous long-term costs on the societies that must maintain and replace them. The recognition that the modern incentive structure produces suboptimal outcomes in the long term is one of the most important lessons of the Roman concrete story. The development of new incentive structures that reward long-term thinking and that account for the full life cycle costs of construction projects is a challenge that the modern world must address if it is to achieve the kind of durable, sustainable infrastructure that the Romans achieved with their concrete. The psychological dimension of the Roman the concrete story is worth exploring. The discovery that an ancient material is superior to a modern one in a critical respect challenges the narrative of progress that is fundamental to the modern worldview. The modern world is deeply invested in the belief that the present is better than the past, that the products of modern technology are superior to the products of ancient craftsmanship, and that the trajectory of human civilization is always upward. The Roman concrete story challenges all of these beliefs, and the challenge is uncomfortable for a civilization that defines itself in terms of its technological superiority. The discomfort that the Roman concrete story provokes is not merely psychological. It has practical consequences, because it undermines the confidence of the construction industry in the materials and the techniques that it has been using for 2 centuries. The recognition that Portland cement concrete is fundamentally inferior to Roman concrete in terms of durability forces the industry to confront the possibility that it has been using the wrong material, that the billions of tons of Portland cement that have been produced and placed since the early 19th century represent not a triumph of modern technology, but a 200-year mistake. This recognition is difficult to accept, and the resistance of the construction industry to the lessons of Roman concrete is partly a consequence of this difficulty. The industry has enormous investments in Portland cement production, in the supply chains that support it, in the standards and specifications that govern its use, and in the training programs that teach its application. The adoption of Roman-inspired alternatives would require the restructuring of these investments, a process that is expensive, disruptive, and uncertain. The inertia of the industry is therefore partly economic and partly psychological, a reluctance to change that is rooted both in the cost of change and in the difficulty of acknowledging that the current approach has been, in a fundamental sense, wrong. The recognition of the superiority of the Roman approach should not be seen as a defeat for modern science and technology, but as an opportunity. The understanding of why Roman concrete is superior, which has been achieved through the application of modern analytical techniques and modern scientific reasoning, is itself a triumph of modern science. The ability to identify the specific mineral phases, the specific chemical reactions, and the specific mechanisms that give Roman concrete its extraordinary durability is a capability that the Romans themselves did not possess, and it is this modern scientific understanding that will enable the development of new materials that incorporate the principles of the Roman approach. While meeting the specific requirements of modern construction, the modern world has something that the Romans did not have: the ability to understand why their material worked, and the ability to use that understanding to develop improved versions. The Romans had the recipe, but they did not have the theory. The modern world has the theory, and it is using the theory to reconstruct and to improve upon the recipe. The combination of the ancient recipe and the modern theory has the potential to produce a material that is superior to both the original Roman concrete and the modern Portland cement concrete, a material that combines the durability of the ancient approach with the precision and the consistency of the modern approach. The question of whether the self-healing property of Roman concrete could be replicated in modern concrete at an industrial scale is one of the most important practical questions in the field. The Mazik team's experiments have demonstrated that the hot mixing technique can produce self-healing concrete in the laboratory, but the translation of this technique to industrial-scale production presents challenges that have not yet been fully resolved. The hot mixing technique involves the addition of quicklime to the concrete mix, a process that is potentially hazardous because of the heat generated by the exothermic reaction between quicklime and water. The management of this heat, which can reach temperatures that are dangerous to workers and that can damage the concrete if not properly controlled, requires the development of mixing procedures and equipment that are specifically designed for the hot mixing process. The development of commercial self-healing concrete products is being pursued by several companies and research institutions, and the first products, based on the Roman-inspired hot mixing technique, are expected to reach the market in the coming years. The commercial viability of these products will depend on their ability to demonstrate superior durability in real-world applications, their compatibility with existing construction practices and standards, and their cost-effectiveness relative to conventional Portland cement concrete. The potential market for self-healing concrete is enormous, encompassing virtually every application in which the durability and the maintenance cost of concrete structures are significant concerns. The infrastructure sector, which includes bridges, highways, tunnels, dams, and other large-scale concrete structures, is the most obvious market for self-healing concrete because the cost savings from reduced maintenance and extended lifespan would be substantial. The marine construction sector, which faces the most severe challenges of concrete durability, is another important market where the superior performance of pozzolanic, self-healing concrete would be particularly valuable. The question of how long it will take for Roman-inspired concrete to become the standard practice in the construction industry is difficult to predict, but the pace of adoption is likely to be influenced by several factors, including the results of field tests and pilot projects, the development of standards and specifications for the new materials, the willingness of regulatory authorities to approve their use, and the economic incentive for builders to adopt them. The history of innovation in the construction industry suggests that the adoption of new materials is typically slow, measured in decades rather than years, because of the conservative nature of the industry and the long lifespan of the structures that are built with the current materials. But the pressure for change is growing. The cost of maintaining the deteriorating concrete infrastructure of the modern world is becoming unsustainable. The environmental impact of Portland cement production is becoming unacceptable. And the evidence that a fundamentally better approach to concrete production is possible, an approach that was demonstrated by the Romans 2,000 years ago, and that is now being validated by modern science, is becoming overwhelming. The question is not whether Roman-inspired concrete will be adopted by the modern construction industry. The question is when. The societal implications of a construction material that lasts for millennia rather than decades extend well beyond the economics of infrastructure maintenance. A civilization that builds with durable materials is a civilization that invests in the future, that creates assets that serve not just the present generation, but many generations to come. The Roman roads, the Roman aqueducts, the Roman harbours, and the Roman public buildings were investments in a future that the Romans could not see, but that they believed was worth building for. The durability of their construction is a testament to the value they placed on the future and to the responsibility they felt toward the generations that would come after them. The modern world, which builds with materials that deteriorate within decades, makes a very different statement about its relationship with the future. The modern approach to construction is essentially disposable, producing structures that are designed to be used for a limited period and then demolished and replaced. This disposable approach reflects the short-term economic thinking that characterizes modern capitalism, and it imposes enormous costs on future generations, who must bear the expense of replacing the infrastructure that the current generation has allowed to deteriorate. The adoption of more durable construction materials, inspired by the principles of Roman concrete, could change this dynamic. A construction industry that produced structures with lifespans measured in centuries rather than decades, would be making a fundamentally different investment in the future, creating assets that would serve many generations and that would reduce the burden of infrastructure maintenance and replacement that the current approach imposes on future generations. The development of such materials is therefore not merely a technical challenge. It is a moral imperative, a responsibility that the current generation owes to the generations that will follow. The Roman builders understood this responsibility, even if they expressed it in different terms than we would use today. They built for eternity, not because they expected their empire to last forever, but because they believed that the structures they built should outlast the builders who built them and the rulers who commissioned them. The durability of their concrete is the physical expression of this belief, a belief that has been vindicated by 2,000 years of history, and that remains as relevant today as it was when the builders of the Pantheon poured the first course of concrete into the formwork of the dome. The question of intergenerational responsibility that the Roman concrete story raises is one that extends beyond the specific domain of construction materials to the broader question of how societies manage their obligations to future generations. What does the story of Roman concrete mean for our understanding of the relationship between ancient and modern technology, between empirical craft and theoretical science, and between the short-term optimization that characterizes modern industry and the long-term durability that characterized the Roman approach? The first implication is a recognition that the modern world does not have a monopoly on technological excellence. The story of Roman concrete demonstrates that ancient civilizations were capable of producing materials and structures that are, in at least some respects, superior to their modern counterparts. This recognition does not diminish the achievements of modern materials science, which has produced an extraordinary range of materials with properties that the Romans could not have imagined. But it does challenge the assumption that modern technology is always superior to ancient technology, an assumption that is deeply embedded in the culture of the modern world, and that is contradicted by the evidence of the Roman concrete structures that have outlasted every modern concrete building. The second implication is a recognition of the value of long-term thinking in technology and in construction. The Romans built their structures to last for centuries, and they invested the time, the effort, and the resources that were needed to achieve this goal. Modern construction, by contrast, is typically designed to last for decades, a time frame that reflects the economic pressures and the short-term thinking that characterize the modern construction industry. The Roman approach, which prioritized durability over speed and cost, produced structures that have saved far more in maintenance and replacement costs over their lifetimes than the additional investment that was required to build them. The modern approach, which prioritizes speed and cost over durability, produces structures that are cheaper to build but far more expensive to maintain and to replace over their lifetimes. There is a pause worth taking here. Consider the Pantheon, standing in the center of Rome, its dome intact after nearly 2,000 years, its concrete stronger today than when it was poured. Consider the modern buildings that surround it, many of which have been built, deteriorated, demolished, and rebuilt multiple times during the Pantheon's lifetime. Consider the resources, the energy, the materials, the labor, the money that have been consumed by the construction and the reconstruction of these modern buildings, and compare them with the single investment that was made in the construction of the Pantheon. The comparison suggests that the Roman approach, which invested more in the initial construction, but which produced a structure that required virtually no maintenance for 2,000 years, may have been more economically efficient than the modern approach, which saves on initial construction, but which requires constant maintenance and periodic replacement. The third implication is a challenge to the modern approach to knowledge management in the construction industry. The Roman concrete recipe was lost because the knowledge was embedded in an institutional infrastructure that collapsed when the Roman Empire declined. The modern construction industry faces similar risks because much of the knowledge that sustains the industry is embedded in specific institutions specific supply chains, and specific training programs that are vulnerable to disruption. The concentration of cement production in a relatively small number of companies, the dependence on specific raw materials from specific geographical sources, and the reliance on specific training programs and certifications for the transmission of construction skills are all potential vulnerabilities that could, under the right circumstances, lead to disruptions comparable to those that caused the loss of Roman concrete. The fourth implication is a recognition of the environmental responsibility that accompanies the choice of building materials. The production of Portland cement is one of the most carbon-intensive industrial processes in the world, and the continued reliance on Portland cement as the primary cementitious material in concrete is incompatible with the goal of reducing global carbon dioxide emissions to levels that are consistent with the prevention of catastrophic climate change. The Roman approach, which used volcanic ash and other pozzolanic materials that require less energy to produce and that generate less carbon dioxide, offers a model for a more environmentally sustainable approach to concrete production. The adoption of pozzolanic cements and supplementary cementitious materials, which reduce the amount of Portland cement required in the concrete mix, and which thereby reduce the carbon emissions associated with concrete production, is one practical step that the construction industry can take toward a more sustainable approach. The development of entirely new cementitious materials, inspired by the chemistry of Roman concrete but adapted to the requirements of modern construction, is a longer-term goal that could ultimately transform the concrete industry and its environmental impact. The economic implications of the Roman concrete research are significant. The global concrete infrastructure is deteriorating at a rate that is generating enormous economic costs, and the development of more durable concrete materials could generate enormous economic savings. The self-healing concrete that has been inspired by the Roman example could significantly reduce the maintenance costs of concrete structures, and the extended lifespan of structures built with more durable materials could reduce the frequency and the cost of replacement. The potential economic benefits of these improvements are measured in the trillions of dollars, making the research on Roman concrete one of the most potentially valuable areas of materials science research in the modern world. The story of Roman concrete is also a story about the importance of interdisciplinary research. The understanding of Roman concrete has required the collaboration of chemists, geologists, materials scientists, structural engineers, archaeologists, and ancient historians, each of whom has contributed expertise and perspectives that are essential for the comprehensive understanding of the material. The success of this interdisciplinary approach, which has produced discoveries that no single discipline could have achieved alone, provides a model for the investigation of other complex problems that span the boundaries of traditional academic disciplines. The geopolitical dimension of the Roman concrete story deserves attention. The dependence of the global construction industry on Portland cement creates a strategic vulnerability that is analogous to the dependence of the global energy system on fossil fuels. The production of Portland cement is concentrated in a relatively small number of countries, and the raw materials, including limestone and clay, are abundant but require significant energy inputs for processing. The energy required for cement production is typically provided by fossil fuels, creating a dependence on the fossil fuel supply chain that adds to the strategic vulnerability of the cement industry. The development of alternative cementitious materials, including pozzolanic cements and geopolymer cements that use locally available materials and that require less energy for production, could reduce this strategic vulnerability by diversifying the supply chain for construction materials. The use of locally available volcanic ash, fly ash, or slag as partial replacements for Portland cement would reduce the dependence on the centralized cement production facilities and on the fossil fuels that power them, increasing the resilience of the construction industry and reducing its vulnerability to supply chain disruptions. The potential for technology transfer from the developed world to the developing world is another important dimension of the Roman concrete story. Many of the developing countries that are experiencing rapid urbanization and that need large quantities of concrete for construction have access to volcanic ash or to other pozzolanic materials that could be used as alternatives to Portland cements. The adoption of pozzolanic concrete in these countries could reduce the cost and the environmental impact of construction while producing more durable structures that would serve their populations for centuries rather than decades. The cultural dimension of the Roman concrete story connects to the broader question of how societies relate to their built environment and to the infrastructure that sustains them. The Roman approach to construction, which prioritized durability and permanence, reflected a cultural orientation that valued the long-term well-being of the community, and that was willing to invest in infrastructure that would serve future generations. The modern approach to construction, which prioritizes speed and cost over durability, reflects a different cultural orientation, one that is focused on the short-term needs of the present, and that discounts the long-term costs that will be borne by future generations. The question of which cultural orientation produces better outcomes for society is one that the Roman concrete story answers with striking clarity. The Roman approach, which invested more in initial construction, but which produced structures that lasted for millennia, has delivered an enormous return on investment, providing utility and beauty and inspiration for nearly 2,000 years. The modern approach, which saves on initial construction, but which requires constant maintenance and periodic replacement, has delivered a much smaller return on investment, consuming far more resources over the long term than the initial savings justified. The recognition that the Roman approach was, in many respects, superior to the modern approach does not mean that the modern construction industry should abandon all of its current practices and revert to Roman methods. The modern industry produces structures that are designed for specific modern purposes, using materials and techniques that are adapted to the specific requirements of modern construction. But the recognition that the principles of Roman concrete, the use of pozzolanic reactions, the incorporation of self-healing mechanisms, the optimization for long-term durability, are superior to the principles of modern concrete should motivate the adoption of these principles in modern practice, adapted to the materials and the techniques that are available in the modern world. The educational implications of the Roman concrete story are significant. The story provides a powerful case study for teaching students about the history of technology, the chemistry of materials, the engineering of structures, and the relationship between technology and society. The multidisciplinary nature of the Roman concrete research, which spans chemistry, geology, archaeology, engineering, and history, makes it an ideal subject for interdisciplinary education, and the practical relevance of the research for the modern construction industry gives the subject an immediacy that is often lacking in purely historical or purely scientific topics. The story of Roman concrete also provides a valuable corrective to the teleological bias that often characterizes the teaching of the history of science and technology. The assumption that the history of science and technology is a story of continuous progress, in which each generation builds upon the achievements of its predecessors and surpasses them, is deeply embedded in the culture of modern education, and it can create a false sense of superiority over the achievements of the past. The Roman concrete story challenges this assumption, demonstrating that ancient civilizations were capable of achievements that the modern world has not yet matched, and that the trajectory of technological development is not always forward. The international dimension of the Roman concrete research community reflects the global significance of the concrete infrastructure problem and the global interest in the development of more durable and more sustainable concrete materials. Research groups in the United States, in Italy, in Germany, in the United Kingdom, in Japan, in China, and in many other countries are actively engaged in the study of Roman concrete and in the development of modern materials that incorporate its principles. The international character of the research community ensures that the results of the research are widely disseminated, and that the insights gained by researchers in one country are available to researchers and practitioners in other countries. The collaboration between the academic research community and the construction industry is an essential component of the effort to translate the lessons of Roman concrete into practical application. The academic researchers have produced the scientific understanding that is needed to develop new materials, but the translation of this understanding into commercial products requires the involvement of the industry, which has the expertise, the facilities, and the market access that are needed to produce and to distribute new materials at scale. The symbolic dimension of the Roman concrete story should not be overlooked. The Pantheon, the most famous and the most perfectly preserved Roman concrete structure, has served as a symbol of human achievement and human aspiration for nearly 2,000 years. The building has inspired architects, engineers, artists, and philosophers across the centuries, and its dome, which was the model for the domes of the Renaissance and the Baroque periods, has been one of the most influential architectural forms in the history of Western civilization. The concrete that supports this dome is therefore not merely a construction material, it is the physical foundation of one of the most important cultural monuments in the history of humanity. The Pantheon stands in the center of Rome, as it has stood for nearly 2,000 years. Its dome, the largest unreinforced concrete dome in the world, curves overhead, its surface marked by the coffers that the Roman builders carved into the wet concrete 19 centuries ago. The oculus at the apex of the dome opens to the sky, admitting a column of light that moves across the interior as the sun travels across the heavens, a clock of light that has been marking the hours since the reign of the Emperor Hadrian. The concrete of the dome is not failing, it is not cracking, it is not spalling, it is not losing its strength. It is, by all available evidence, stronger today than it was when it was poured, strengthened by 2 millennia of chemical reactions that have filled its pores and healed its cracks and densified its matrix, reactions that are still occurring, reactions that will continue for centuries or millennia to come. The dome is not merely surviving, it is alive in a chemical sense, a material that is still evolving, still changing, still growing stronger with the passage of time. The concrete of the modern world does not share this vitality. The bridges and the highways and the buildings and the dams that constitute the infrastructure of modern civilization are slowly falling apart, their concrete cracking, their steel corroding, their structural integrity diminishing with each passing year. The cost of maintaining this infrastructure is enormous, and the cost of replacing it is almost beyond comprehension. And yet the Romans, working with volcanic ash and lime and water, with no knowledge of chemistry and no understanding of the processes that gave their material its remarkable properties, produced a concrete that has outlasted everything we have built and that shows no signs of failing. The math is striking. Modern concrete lasts 50 to 100 years. Roman concrete has lasted 2,000 years and counting. The ratio is at least 20 to 1, and it may ultimately prove to be far greater. The modern approach produces approximately 8% of global carbon dioxide emissions. The Roman approach produces a fraction of that. The modern approach requires constant maintenance and periodic replacement. The Roman approach requires virtually none. By every measure of long-term performance and environmental responsibility, the ancient approach is superior to the modern one. The story of Roman concrete is a story about humility. It is a story that reminds us that the modern world, for all its scientific knowledge and technological sophistication, does not always produce the best solutions to practical problems. It is a story that demonstrates that empirical knowledge, the knowledge that is acquired through centuries of practical experience, can sometimes surpass the knowledge that is produced by scientific analysis and theoretical reasoning. And it is a story that challenges us to learn from the achievements of the past, to recognize that the people who came before us were capable of extraordinary things, and to apply their insights to the problems that we face today. The recipe for Roman concrete was lost for 1,500 years. It is now being rediscovered, piece by piece, through the patient work of scientists who are analyzing the ancient material and who are beginning to understand the extraordinary chemistry that gives it its remarkable properties. The rediscovery is not yet complete. The specific recipe that the Romans used, with all its variations and all its nuances, has not yet been fully reconstructed. But the principles that underlie the recipe, the pozzolanic reaction, the self-healing mechanism, the long-term mineral growth, are now understood, and they are being applied to the development of modern concrete materials that may one day approach the durability and the sustainability of the Roman original. The Pantheon watches and waits, patient in its perfection, its dome a monument to a knowledge that was lost and that is slowly being found again. The concrete remembers what we forgot. The chemistry continues what the builders began, and the dome, the most magnificent concrete structure ever built by human hands, stands as proof that the best of the past can be better than the best of the present, and as a challenge to make the future worthy of the past. The Romans built for eternity. The concrete they poured is still setting, still strengthening, still fulfilling the purpose for which it was made. 2,000 years have passed, and the Pantheon has not finished becoming what its builders intended it to be. The concrete is still working, the chemistry is still active, the building is still alive, and somewhere in the laboratories and the workshops of the modern world, researchers are learning, slowly and painstakingly, how to make concrete that will do what the Roman concrete has done: endure. The light that enters through the oculus of the Pantheon has been making its daily circuit of the interior for nearly 2,000 years. The beam of sunlight that moves across the walls and the floor of the temple is a clock that has been keeping time since the 2nd century of the Common Era, marking the hours and the seasons and the centuries with a regularity that has outlasted empires, survived wars, and persisted through every change that the world has undergone since the builders placed the last course of concrete and removed the last piece of formwork from the dome. The oculus is open to the sky. It admits rain as well as light, and the rain that falls through the opening onto the marble floor of the interior is drained away through channels that were cut into the floor by the Roman builders. The concrete of the dome, which is exposed to the weather through the oculus, has been subjected to 2,000 years of rain, of sun, of wind, of freezing and thawing, and it has survived without significant damage. The surface of the dome shows the marks of age, but the structural integrity of the concrete is undiminished. The material is doing what it was made to do. It is enduring. The engineers and the scientists who study the Pantheon today bring instruments and techniques that the Roman builders could not have imagined. X-ray diffractometers, scanning electron microscopes, synchrotron radiation sources, computational modeling software. They apply these tools to the concrete of the dome, reading the mineral phases, the chemical compositions, the microstructural features that the builders created without knowing what they were creating. The scientists are learning the language of the concrete, decoding the chemical text that the builders wrote in lime and ash and water, a text that has been waiting for 2,000 years to be read. The reading of that text is one of the great scientific adventures of our time. Every analysis reveals new information. Every discovery deepens the understanding of how the Roman builders achieved what they achieved and why their achievement has endured. The story is not finished. The text has not been fully decoded, but the reading continues, and each new chapter that is deciphered brings us closer to the understanding that will allow us to build as the Romans built, to make concrete that will endure as Roman concrete has endured, and to construct a world that is worthy of the example that the Pantheon has set. Every year, millions of tourists visit the Pantheon, passing through the massive bronze doors into the circular interior, tilting their heads back to gaze up at the dome that has sheltered this space for nearly 2,000 years. Most of them admire the beauty of the building, the proportions of the space, the drama of the light that enters through the oculus. Few of them think about the concrete, about the material that makes the building possible, about the chemistry that has sustained the structure through 20 centuries of history. The concrete is invisible, hidden behind the marble and the stucco that decorate the interior, supporting everything, sustaining everything, enduring everything, and asking nothing in return. But the concrete is the real story. The marble can be replaced. The stucco can be repaired. The bronze doors can be recast. The concrete cannot be replaced because it is the building. It is the structure that holds everything together, the material that bears the weight and the weather and the years. And it is the material that has proven, beyond any possibility of doubt, that the builders of the ancient world knew something about concrete that the builders of the modern world have forgotten, something that we are only now, after 1500 years of forgetting, beginning to remember. The concrete of the Pantheon is not a relic. It is not a museum piece. It is a living material, a material that is still actively engaged in the chemical processes that sustain its strength and its integrity. The pozzolanic reactions that began when the Roman builders mixed their lime and their volcanic ash 19 centuries ago have not stopped. They have continued, slowly and steadily, for 2,000 years, filling the pores and the voids in the concrete with new mineral phases, healing the cracks that earthquakes and weather have produced, and strengthening the material with each passing century. This is the final lesson of the Roman concrete story, that the best materials are not the ones that resist change, but the ones that embrace it, not the ones that fight the passage of time, but the ones that use the passage of time to grow stronger. The Roman concrete does not merely endure, it improves. It is a material that is in partnership with time, using the centuries as a resource, rather than suffering them as a burden. And in this partnership, in this collaboration between material and time, lies the secret that the Roman builders knew and that the modern world is only now beginning to learn.